We are smaller than we think. And that is not a metaphor. The universe is 93 billion light-years across. We can see only 4% of what actually exists. And the James Webb Space Telescope just found galaxies that break every rule we built to explain where we came from. Galaxies too big, too bright, too organized for the age they claim. Galaxies that should not exist, but they do. And the more Webb looks into the abyss of deep space, the more the abyss stares back with something we did not expect. Structure, patterns, a cosmic scaffolding so vast it resembles the neural pathways inside your own brain. 2 trillion galaxies threaded together across unthinkable distances, held in place by forces we cannot see, pulled apart by an energy we cannot name. Dark energy. An invisible hand accelerating the expansion of everything at 46 miles per second per megaparsec. And it is winning. Right now, as you sit here, 94% of the cosmos is slipping beyond the horizon of what we will ever be able to reach. Not because our telescopes are too weak, not because our ships are too slow, but because the universe itself is running away from us faster than light can catch it. So what does that make us? A cosmic accident clinging to a pale blue dot in an ocean of darkness we will never fully know? Or something else? Something rarer, the only part of the universe, as far as we can tell, that has opened its eyes and looked back at itself. This is the story of what Webb found when it looked deeper than any instrument in history, and what it means that we are here, awake and aware, in a cosmos too large to comprehend and too strange to ignore. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. The universe is 93 billion light-years across. Let that sit for a second. 93 billion, not million, not trillion in terms of miles or kilometers, but light-years, the distance light itself travels in a full year at a speed of 300,000 kilometers per second. Light could circle the Earth 7.5 times in 1 second. In a year, moving at that speed without ever slowing down or stopping, it covers about 9.5 trillion kilometers. Now multiply that by 93 billion. That is the size of the observable universe, the canvas we are standing on. The stage where every star you have ever seen, every galaxy ever photographed, every quasar, every nebula, every black hole, every planet, every atom in your body has played out its existence. And here is the part that should bother you. That number, as staggering as it is not the size of the universe. It is only the size of the part we can see. The universe you are standing in right now could be 10 times larger. It could be 1,000 times larger. It could be infinite. We do not know. We cannot know. Not yet. Not with the tools we have. What we call the observable universe is not a measure of how big the cosmos actually is. It is a measure of how far light has been able to travel since the beginning of time. It is the edge of our cage, and the bars are made of physics. When astronomers say the universe is 93 billion light-years in diameter, they are not guessing. This is a calculated number based on the age of the universe, the speed of light, and the rate at which space itself has been expanding since the Big Bang. The universe is about 13.8 billion years old. You would think that means we should only be able to see 13.8 billion light-years in every direction. A sphere with a radius of 13.8 billion light-years, that would give us a total diameter of about 27.6 billion light-years. Simple math. Except the universe does not do simple math. Because while light was traveling toward us from distant galaxies, the space between us and those galaxies was stretching. The fabric of the cosmos itself was expanding, pulling everything apart. So by the time that light finally reached Earth, the objects that emitted it had moved much farther away than they were when the light began its journey. The photons we detect today from the most distant galaxies left their sources when those galaxies were only a few 100 million light-years away from the patch of space that would one day become our solar system. But in the billions of years it took for that light to cross the universe, space expanded so much that those galaxies are now more than 46 billion light-years away. Multiply by 2 to account for all directions, and you get 93 billion light-years, edge to edge. The observable universe is not defined by where things are. It is defined by how far their light has managed to travel through an expanding cosmos. That distinction matters because it means the edge of the observable universe is not a wall, it is a horizon. Stand on a beach and look out at the ocean. You can see about 5 kilometers to the horizon before the curve of the Earth cuts off your view. That does not mean the ocean ends 5 kilometers away. It means your perspective ends. Walk forward, and the horizon moves with you. New water comes into view. The same thing happens in cosmology. The observable universe is the view from here, from Earth, from this moment in time. If you could somehow instantly teleport to a galaxy 40 billion light-years away and look around, you would see a completely different observable universe centered on that new location. Some of the galaxies visible from Earth would have disappeared beyond your new horizon, and entirely new galaxies currently beyond our view would come into sight. The true universe, the whole universe, does not care about horizons. It exists whether we can see it or not, and every credible model of cosmology suggests it extends far beyond what we have access to. How far, we do not know. Whether it has an edge at all, we do not know. This is not a new frustration. Humans have been trying to measure the cosmos for thousands of years, and every time we thought we had it pinned down, the universe turned out to be bigger than we assumed. The ancient Greeks believed the stars were fixed to a crystalline sphere that rotated around the Earth. Aristarchus of Samos tried to calculate the distance to the Sun and the Moon using geometry. He got the method right, but the numbers wrong, by a factor of about 20. Still, for someone working in the 3rd century BC with no telescopes, no cameras, and no concept of light years, getting even the scale of the solar system approximately correct was an astonishing achievement. For most of human history, the Milky Way was assumed to be the entire universe, a flat disk of stars with Earth somewhere near the middle, surrounded by darkness. That view held until the early 20th century, when astronomers started arguing about what the so-called spiral nebulae actually were. Fuzzy patches of light scattered across the night sky. Some believed they were clouds of gas within our own galaxy. Others suspected they were separate galaxies entirely, island universes millions of light-years away. The debate was so heated that in 1920, 2 prominent astronomers, Harlow Shapley and Heber Curtis, held a formal public debate at the Smithsonian in Washington. Shapley argued the Milky Way was enormous and the spiral nebulae were local. Curtis argued the opposite, that the nebulae were distant galaxies and the universe was far larger than anyone had imagined. Neither man had definitive proof. The technology to settle the question did not exist yet. Then in 1923, Edwin Hubble, working at the Mount Wilson Observatory in California, turned the Hooker telescope, the largest in the world at the time, toward the Andromeda Nebula. He found something no one had seen before: individual stars. Not just stars, but a specific type called Cepheid variables. These stars pulsate in brightness at a rate directly tied to their true luminosity. Measure how fast a Cepheid blinks, and you know how bright it actually is. Compare that to how bright it looks from Earth, and you can calculate how far away it is. Hubble did the math. Andromeda was not a nebula, it was a galaxy, and it was roughly 900,000 light-years away, far beyond the borders of the Milky Way. That number has since been revised upward to about 2.5 million light-years, but the point stood. The universe was not one galaxy, it was filled with them. Hubble kept looking. Within a few years, he had measured the distances to dozens of galaxies, and he noticed something strange. Almost all of them were moving away from us. The farther away a galaxy was, the faster it was receding. The universe was not static, it was expanding. That observation, published in 1929, became the foundation of modern cosmology. It also kicked off a new problem. If the universe is expanding, how fast? Hubble calculated a number for the expansion rate, now called the Hubble constant. His first estimate was so wildly off that it made the universe appear younger than the Earth, which obviously did not work. For decades, astronomers fought over the correct value. Two camps formed. One believed the constant was close to 50 kilometers per second per megaparsec. The other insisted it was closer to 100. A megaparsec, by the way, is about 3.26 million light-years. The disagreement was not academic. If the expansion rate was 50, the universe was older and larger. If it was 100, the universe was younger and smaller. Entire cosmological models hinged on which number was right. The argument persisted for more than half a century. By the early 2000s, the value had finally converged to around 70, give or take. The war seemed over. Except it was not, because as instruments got better, a new split appeared. Measurements of the early universe using data from the cosmic microwave background gave one answer. Direct measurements of nearby galaxies using the distance ladder gave a different answer. That tension is still unresolved, and as we will see later, the James Webb Space Telescope has made it worse, not better. But before Webb, before Hubble the telescope, before Hubble the man, the question was simpler. How big is the universe? And the only honest answer has always been bigger than we thought. Every new telescope, every new technique, every new discovery has pushed the boundary outward. When Hubble found that Andromeda was a separate galaxy, the known universe expanded by millions of light-years overnight. When astronomers began mapping distant quasars and galaxy clusters in the 1960s and 70s, the scale jumped again. When the Hubble Space Telescope launched in 1990 and started imaging galaxies billions of light-years away, we realized the cosmos was not just big. It was incomprehensibly vast, and it was full. Everywhere Hubble pointed, it found galaxies, thousands of them, tens of thousands. In some of the deepest images ever taken, tiny patches of sky no larger than a grain of sand held at arm's length, Hubble found 10,000 galaxies in a single frame. Each galaxy containing hundreds of billions of stars, each star potentially hosting planets, each planet a world with its own geology, its own chemistry, its own history. That is when astronomers realized they needed a census, not a guess. Not an estimate, a full accounting of what is actually out there. How many galaxies exist in the observable universe? How are they distributed? How did they form? When did they form? What do they look like at different distances? Which is the same as saying, what did they look like at different points in cosmic history? Answering those questions requires more than just pointing a telescope at random patches of sky and counting dots. It requires surveys, massive, coordinated observing programs that map the sky in sections, catalog every object, measure every distance, record every spectrum. Hubble did this for decades. The Sloan Digital Sky Survey did this from the ground, mapping millions of galaxies across a huge portion of the northern sky. And now, the James Webb Space Telescope is doing it with a precision and depth that makes everything before it look like a rough draft. Webb is not just taking pictures, it is conducting a cosmic census. One of its largest observing programs in its first year of operation was called Webb, a survey that used more than 200 hours of telescope time and captured more than 10,000 individual exposures. The result was a map containing nearly 800,000 galaxies spread across a region of sky about the width of 3 full moons placed side by side. That might not sound like much, 3 full moons. But in cosmic terms, that is an enormous field of view. And the galaxies Webb found were not all nearby. Many of them are so distant that their light has been traveling toward us for more than 13 billion years. We are seeing them as they existed when the universe was still in its infancy, less than 1 billion years old. The survey found 10 times more galaxies in these early epochs than astronomers had anticipated. 10 times. That is not a minor adjustment. That is a fundamental reassessment of how quickly galaxies formed after the Big Bang. Jehan Kartal-Tepe, an astrophysicist at the Rochester Institute of Technology and one of the lead researchers on Webb, said plainly that she does not know if the James Webb Space Telescope will ever cover an area of this size again. The dataset, she said, will be used for many years. It is a reference, a benchmark, a cosmic phone book that future astronomers will return to again and again as they try to piece together the history of the universe. And this is just one survey. Webb is running dozens of others, each designed to answer different questions. Some focus on the earliest galaxies, others hunt for planets around nearby stars, some map the structure of distant nebulae. Others search for the chemical signatures of life in the atmospheres of exoplanets. The telescope is pulling in so much data that analysis will take years, decades even. But the central mission, the thing Webb was built to do above all else, is to push the edge of the observable universe as far back as physics will allow, to see the first light, to catch the moment when stars ignited for the first time and galaxies began to assemble from clouds of primordial hydrogen, to look at the universe when it was not 93 billion light-years across, but a fraction of that size, hotter, denser, simpler, and yet, as Webb has already shown, not simple at all. Because the James Webb Space Telescope is not just mapping the observable universe, it is revealing that the observable universe, vast as it is only a sliver of reality. 93 billion light-years sounds infinite to a species that has only existed for a few 100,000 years on a planet 8,000 miles wide. But in cosmological terms, it is a bubble, a local pocket of space whose light has had just enough time to reach us. Beyond that bubble, the universe continues. Galaxies we will never see are forming, evolving, colliding, dying. Stars are being born in clouds of gas that will never send a single photon in our direction. Planets are cooling, atmospheres are thickening, perhaps life is starting, all of it happening in a region of space that is, for us, permanently invisible. Not because it is too faint, not because our telescopes are not good enough, but because the light has not had time to get here yet. And in an accelerating universe, some of that light never will. The cosmos is expanding faster than light can cross it, which means the observable universe is not just the only part we can see. It is, in a very real sense, the only part we will ever be able to see. The rest is out there. We just cannot reach it. And that raises a question that should keep anyone awake at night. If everything we have ever observed, every galaxy, every star, every particle of light, exists within a bubble 93 billion light-years wide, and that bubble is only a small fraction of the true universe, what else is out there? What are we missing? What is happening beyond the horizon that we have no language for, no theory for, no way to even begin imagining? The James Webb Space Telescope cannot answer that question. No instrument ever built can. But what Webb can do, what it is doing right now, is show us the very edge of what is possible to know. It is pulling back the veil on the earliest moments of cosmic history, imaging galaxies that formed when the universe was barely out of its cradle, and in doing so, it is revealing something deeply unsettling. The universe, even the observable universe, is stranger than we thought. A glimpse of Genesis, Webb's window to the first light. The James Webb Space Telescope is not looking at the universe, it is looking at the past. Every photon that hits its mirrors is ancient. Some of them are older than Earth, older than the Sun, older than the atoms in your bones. They have been traveling through space for more than 13 billion years, crossing distances so vast that the galaxies they came from have long since drifted beyond any possibility of contact. By the time those photons arrive at Webb's gold-plated mirrors, they are not just light, they are evidence, fossils of a universe that no longer exists in the form we are seeing it. This is not a metaphor. Webb is a time machine, not in the way science fiction imagines time machines with spinning dials and sparking consoles, but in the way physics allows. Light moves at a fixed speed, 300,000 kilometers per second, fast by human standards, glacial by cosmic ones. When you look at the sun, you are seeing it as it was 8 minutes ago. That is how long it takes light to cross the 150 million kilometers between the sun and Earth. Look at the nearest star beyond our solar system, Proxima Centauri, and you are seeing it as it was 4 years ago. Look at the Andromeda galaxy, and you are seeing light that left 2.5 million years ago, when early humans were just beginning to chip stones into tools. Look farther, and the delays stretch into billions of years. The light Webb detects from the most distant galaxies left its source when the universe was less than 400 million years old. We are not observing those galaxies as they are today. We are observing them as they were 13.4 billion years ago. By now, those galaxies have aged, evolved, merged with others, or been torn apart, but we will never see that. The light carrying that information is still on its way and will not arrive for billions of years, assuming we are still around to catch it. Webb was designed specifically to catch the oldest light in the universe, not the cosmic microwave background, which is older but tells a different story. Webb is hunting for the first stars, the first galaxies, the moment the universe stopped being a dark fog of hydrogen and began to glow. To do that, it needed to see in infrared. Hubble, for all its brilliance, was built primarily to observe visible and ultraviolet light. That works fine for nearby objects, stars in our galaxy, planets in our solar system, galaxies a few billion light-years away. But the farther you look, the more the expansion of the universe stretches the light traveling toward you. Ultraviolet light from a galaxy in the early universe gets stretched into visible light. Visible light gets stretched into infrared. Infrared gets stretched into the far infrared. By the time the light from the earliest galaxies reaches Earth, it has been redshifted so dramatically that it falls entirely outside the range Hubble was built to detect. Hubble could see hints of these distant objects, faint smudges at the edge of its sensitivity, but it could not resolve them. It could not measure their composition. It could not tell you what they were made of, how old their stars were, whether they contained heavy elements. Webb can. Its instruments are tuned to wavelengths between 0.6 and 28.5 micrometers, covering near-infrared to mid-infrared. That range includes the redshifted light from galaxies formed in the first few 100 million years after the Big Bang. Objects that Hubble could barely glimpse, Webb sees in detail. The telescope itself is an engineering marvel that nearly did not happen. It was proposed in the mid-1990s, approved in the early 2000s, and immediately ran into problems. The design was too ambitious. The budget exploded. The timeline slipped again and again. By the time it finally launched on December 25, 2021, the project had cost $10 billion and taken more than 2 decades to complete. It had survived multiple attempts to cancel it, congressional hearings, public mockery, a reputation as the telescope that would never fly, but it did fly. And 6 months later, after a deployment sequence so complex that a single failed step would have turned the whole mission into $10 billion worth of space junk, it opened its mirrors and began to observe. The primary mirror is 6.5 meters across, nearly 3 times the diameter of Hubble's mirror, but it could not be launched as a single piece. No rocket fairing is that large. So the mirror was built in 18 hexagonal segments, each coated in a microscopically thin layer of gold. Gold reflects infrared light better than aluminium, which is what most telescope mirrors use. The segments were folded up for launch, then unfolded in space and aligned with nanometer precision using actuators on the back of each piece. The alignment process took months. Get it wrong, and the telescope would produce blurry, useless images. They got it right. Webb does not orbit Earth. It sits at a point in space called Lagrange Point 2, about 1.5 million kilometers away from our planet, on the side facing away from the Sun. Lagrange points are locations where the gravitational pull of 2 large bodies, in this case Earth and the Sun, balance out in such a way that a smaller object placed there will stay roughly in position without needing constant thrust. L2 is particularly useful for infrared telescopes because it allows Webb to keep its back to both the Sun and the Earth at all times. That matters because infrared detectors have to stay cold, very cold. Webb's instruments operate at temperatures around -233 degrees Celsius, just 40 degrees above absolute zero. If sunlight or earthlight hit the mirrors or the instruments directly, the heat would blind them. To prevent that, Webb carries a sun shield the size of a tennis court, made of 5 layers of a material called kapton, each layer thinner than a human hair. The shield blocks thermal radiation from the Sun, Earth, and Moon, keeping the telescope cold enough to detect the faint infrared glow of galaxies at the edge of the universe. The sun shield, like the mirror, had to be folded for launch and deployed in space. It took 2 weeks to unfold. Every step was critical. If one membrane snagged or tore, the mission would fail. It deployed perfectly. Once operational, Webb began doing what it was built to do, looking backward. One of its earliest targets was a galaxy cluster called SMACS 0723, located about 4.6 billion light-years from Earth. Galaxy clusters are useful because they act as natural magnifying glasses. Their combined mass warps the space around them so severely that light passing nearby gets bent and focused, a phenomenon called gravitational lensing. This allows telescopes to see objects far behind the cluster that would otherwise be too faint to detect. Hubble used this trick for years in a program called Frontier Fields. Webb took the same approach and pushed it farther. The image Webb produced of SMACS 0723, released in July 2022 as the telescope's first deep field, showed thousands of galaxies scattered across a patch of sky the size of a grain of sand held at arm's length. Some of those galaxies are more than 13 billion light-years away. We are seeing them as they existed less than 1 billion years after the Big Bang. They should be faint, red, primitive. Some of them are, others are not. Some are bright, some show signs of structure, spiral arms, central bulges, features that should take billions of years to develop. This was the first hint that something about our models of early galaxy formation might be wrong. Webb followed that image with deeper observations. One of its longest exposure programs targeted a galaxy cluster called Abell S1063, about 4.5 billion light-years away. The telescope spent more than 120 hours staring at that single patch of sky, collecting every photon it could. The resulting image revealed galaxies so distant and so faint that no previous instrument could have detected them. Some of these galaxies formed when the universe was only a few 100 million years old. That places them squarely in an era astronomers call the epoch of reionization. To understand why that matters, you have to know what came before it. After the Big Bang, the universe was a hot, dense soup of particles, protons, electrons, photons, everything colliding with everything else at speeds high enough to keep atoms from forming. Then, about 380,000 years after the Big Bang, the universe cooled enough for protons and electrons to stick together and form hydrogen, neutral hydrogen. The moment that happened, photons stopped scattering off free electrons and started traveling in straight lines. The universe became transparent for the first time. That is when the cosmic microwave background was released, the afterglow we still detect today. But transparent does not mean bright. The universe had no stars yet, no galaxies, just clouds of neutral hydrogen drifting through darkness. Astronomers call this period the cosmic dark ages. It lasted for tens of millions of years, possibly longer. Gravity was pulling the hydrogen into clumps, but nothing was glowing. Eventually, somewhere between 100 and 250 million years after the Big Bang, the first stars ignited. These stars were unlike anything that exists today. They formed from pure hydrogen and helium, with no heavier elements, because heavier elements did not exist yet. Without metals, which is what astronomers call anything heavier than helium, the gas clouds that collapsed into stars could grow much larger before igniting. Some of the first stars may have been hundreds of times more massive than our Sun. They burned blue and white, ferociously hot, and died within a few million years. When they exploded as supernovae, they seeded the surrounding gas with the first carbon, oxygen, iron, and other heavy elements. Those enriched clouds formed the next generation of stars, slightly smaller and longer-lived. And from those stars, galaxies began to assemble. But the first stars did more than just create heavy elements. Their ultraviolet radiation was so intense that it began to ionize the neutral hydrogen around them, ripping electrons off atoms and turning the fog back into a plasma. This process spread outward like bubbles forming in boiling water. Small ionized regions around the first stars and galaxies expanded and merged until eventually the entire universe was reionized. That transition from neutral to ionized is the epoch of reionization. It is one of the most important events in cosmic history because it is what allowed the universe to become the place we see today. Ionized gas behaves differently than neutral gas. It can cool more efficiently. It can collapse into denser structures. It can form stars at higher rates. Without reionization, galaxy formation would have stalled. The universe would look nothing like it does now. Webb was built to observe this era directly. Hubble could only see the tail end of reionization, catching a few galaxies from when the process was nearly complete. Webb can see earlier, into the thick of it, when the first bubbles of ionized gas were just beginning to form. And what it is finding is both expected and strange. Expected because, yes, there are small, faint galaxies at those distances, exactly the kind of objects that should be driving reionization. Strange because there are also galaxies that are far too bright and far too massive to have formed that quickly. One galaxy candidate detected by Webb, observed as it existed only 350 million years after the Big Bang, appears to contain as much mass as the Milky Way. That should not be possible. The Milky Way took more than 13 billion years to build. This galaxy did it in a few hundred million. Either our models of star formation are incomplete, or something unusual was happening in the early universe that we do not yet understand. More on that in the next chapter. For now, the point is that Webb is not just confirming what we expected, it is forcing us to revise the story. Another unexpected finding came from Webb's spectroscopy. Spectroscopy is the process of splitting light into its component wavelengths to identify what elements are present in the object producing that light. Different elements absorb and emit light at specific wavelengths, creating a unique fingerprint. By analyzing the spectrum of a distant galaxy, astronomers can tell what it is made of, how fast it is moving, how old its stars are, and whether it contains dust and heavy elements. Webb's near-infrared spectrograph has been used to study dozens of early galaxies, and the results have been surprising. Some of the galaxies observed in the first few 100 million years after the Big Bang already contain oxygen and carbon, not in large amounts, but enough to be detectable. That means stars in those galaxies had already lived, died, and enriched their surroundings. The timeline is tight, uncomfortably tight. Stars take time to form, time to burn through their fuel, time to explode. Doing all of that within the first few 100 million years of the universe requires an efficiency that current models struggle to explain. It is not impossible, it is just hard, and the more Webb looks, the more examples it finds. The telescope has also started imaging individual objects that were previously only theoretical. One example is a planet called 29 Cygni b, a gas giant about 15 times the mass of Jupiter orbiting a star 2.8 thousand light-years from Earth. Webb directly imaged this planet, something that is extraordinarily difficult because planets are millions of times fainter than the stars they orbit. The image revealed that the planet's atmosphere contains heavy elements, possibly carbon monoxide or methane. That is useful for understanding how giant planets form and what their atmospheres look like at different distances from their host stars. But it also demonstrates Webb's versatility. The same instrument that can detect galaxies 13 billion light-years away can also analyze the chemistry of a planet in our own galactic neighborhood. That range, from nearby planets to the edge of the observable universe, is what makes Webb the most powerful observatory humans have ever built. Comparing Webb to Hubble is not entirely fair because they were designed to do different things. Hubble was a general-purpose telescope. It could image planets, stars, nebulae, and galaxies across a wide range of wavelengths. It gave us the pillars of creation, the Hubble Deep Field, the first measurements of the universe's expansion rate. It operated for more than 3 decades and produced some of the most iconic images in the history of astronomy. Webb is more specialized. It was built for one job above all others, to see the earliest galaxies, to push the boundary of observation as far back in time as physics allows. It is doing that job better than anyone expected, but it is not replacing Hubble. It is extending Hubble's reach, filling in the gaps that Hubble could not see, revealing details that Hubble could only hint at. The two telescopes complement each other in the same way that different instruments in an orchestra complement each other. Each has a role. Together they create a fuller picture. What Webb is showing us, in image after image, spectrum after spectrum, is that the early universe was not quiet. It was not simple. It was not empty. It was full of galaxies forming faster than they should have. Stars igniting earlier than expected. Heavy elements appearing sooner than models predicted. The cosmic dark ages were shorter than we thought. The epoch of reionization was messier. The The first light did not flicker on gradually, it exploded, and the galaxies that emerged from that explosion are now sitting in Webb's data archives, waiting to be studied in detail. Some of them fit our models, many do not. The ones that do not fit are the ones that matter most, because they are the ones forcing astronomers to ask uncomfortable questions. Questions about how galaxies grow, how stars form, whether the standard model of cosmology is missing something fundamental, whether the universe, in its earliest moments, played by rules we have not discovered yet. The James Webb Space Telescope cannot answer all of those questions, but it is providing the evidence needed to ask them properly. And in some cases, the evidence is so strange that the questions themselves are starting to sound absurd. Which brings us to the next problem: the galaxies that should not exist, the unthinkable. Galaxies that shouldn't exist. The early universe was supposed to be patient. That was the story we told for decades. After the Big Bang, matter spread out, cooled down, and slowly began to clump together under gravity's gentle tug. The first stars took tens of millions of years to ignite. The first galaxies took hundreds of millions more to assemble. They started small, merged gradually, and grew over billions of years into the massive spiral and elliptical galaxies we see today. The Milky Way, our home, spent more than 13 billion years pulling itself together. Most of that time was spent quietly accreting gas, forming stars in bursts and lulls, colliding with smaller neighbors, and building up the structure we recognize now. That timeline felt right. It matched the math. It fit the models. It explained the observations Hubble had been sending back for 3 decades. Then the James Webb Space Telescope opened its eyes and found galaxies that had no interest in waiting. In July 2022, less than 6 months after Webb began science operations, astronomers released an image that should have been routine. It was a gravitationally lensed deep field centered on a galaxy cluster called SMACS 0723. The cluster itself sits about 4.5 billion light-years away, unremarkable by cosmological standards. What made the image extraordinary was what lay behind it. Scattered across the frame, distorted into arcs and streaks by the cluster's gravity, were thousands of galaxies. Some were nearby, some were not. A few of them were so distant that their light had been traveling toward us for more than 13 billion years. We were seeing them as they existed when the universe was less than 1 billion years old. That part was expected. Webb was built to find those galaxies. What was not expected was how bright they were, how structured, how mature. These were not the faint, irregular smudges of proto-galaxies that models predicted. Some of them had spiral arms, central bulges, organized disks, features that should take billions of years to develop, and they were sitting there, fully formed, in a universe that was barely 400 million years old. At first, some astronomers assumed the distances were wrong. Measuring how far away a galaxy is requires determining its redshift, which tells you how much the universe has expanded since the light left its source. For very distant galaxies, that measurement can be tricky. Hubble had run into this problem before. It would spot a faint red object, estimate its redshift based on its color, and later find out it was actually closer than expected, just unusually dusty or dim. The technique is called photometric redshift estimation, and it is prone to errors. Spectroscopy, which splits the light into its component wavelengths and identifies specific absorption or emission lines, is far more accurate. But spectroscopy takes time. You need to stare at an object for hours, sometimes days, to collect enough photons to build a clean spectrum. In the early months of Webb's mission, most of the distance estimates were photometric, educated guesses based on the galaxy's colors and brightness. So when the first round of results came in showing massive galaxies at extreme distances, the cautious response was to wait for spectroscopic confirmation. Maybe these objects were closer than they looked. Maybe the photometric method had misfired. Maybe this was a false alarm. It was not. Over the following months, Webb's near-infrared spectrograph, an instrument capable of measuring the precise wavelengths of light coming from distant galaxies, began confirming the distances. One by one, the candidates held up. These galaxies were exactly where they appeared to be, and they were exactly as massive as they looked. In some cases, they were more massive than anyone had predicted. One galaxy, observed as it existed roughly 350 million years after the Big Bang, appeared to contain as much stellar mass as the Milky Way. Another, seen at around 400 million years, showed signs of a well-developed disk and a central concentration of stars that suggested it had already undergone significant evolution. A third, spotted at just under 300 million years post-Big Bang, was so luminous that some researchers initially suspected it might be harboring an active supermassive black hole at its core, not because there was direct evidence of one, but because no other explanation seemed to fit the brightness. These were not outliers. Webb was finding them everywhere it looked. Deep surveys targeting small patches of sky were turning up dozens of these massive early galaxies. The numbers kept climbing, and with each new detection, the problem became harder to ignore. The problem is time. Galaxies do not assemble overnight. They require several steps, each of which takes time. First, dark matter has to clump together into halos. Dark matter does not emit or absorb light, but it makes up about 85% of the matter in the universe, and its gravity is what pulls normal matter, the hydrogen and helium gas, into place. Once a dark matter halo forms, gas falls into it and begins to cool. As the gas cools, it condenses into clouds dense enough to collapse under their own gravity. Those clouds fragment into smaller clumps, and eventually, if conditions are right, stars ignite. The first stars are massive and short-lived. They burn through their fuel in a few million years and explode as supernovae, enriching the surrounding gas with heavier elements. From that enriched gas, the next generation of stars forms, slightly longer-lived and more stable. Over hundreds of millions of years, those stars and the gas around them settle into a rotating disk or an elliptical cloud, depending on how much angular momentum the system has. Collisions with other small galaxies add mass and complexity. Feedback from supernovae and stellar winds regulates how fast new stars can form, preventing the galaxy from burning through all its gas too quickly. The whole process is a balance between gravity pulling things together and energy from stars and black holes pushing gas apart. That is the standard story, and for nearby galaxies it works. We can trace their histories backward using observations of their stars, their gas content, their chemical abundances. We can watch galaxies at different distances, which is the same as watching them at different ages, and see how their properties change over time. The models built from those observations predict that galaxies in the first few 100 million years after the Big Bang should be small, dim, and chaotic. They should weigh a few million to a few billion times the mass of the Sun. They should have irregular shapes. They should be dominated by young blue stars and mostly free of heavy elements. What Webb is seeing does not match that prediction. Some of the galaxies it has found weigh tens of billions of solar masses. They have organized structures. They contain stars that appear to be hundreds of millions of years old, which means those stars must have formed even earlier, pushing the timeline back further. And some of them show evidence of oxygen, carbon, and other heavy elements in their spectra, which means at least one generation of stars had already lived and died by the time we are observing them. Doing all of that in 300 or 400 million years is not impossible, but it requires nearly everything to go right. The gas has to cool efficiently. Star formation has to proceed at rates much higher than what we see in the modern universe. Feedback mechanisms that normally slow things down have to be weaker or absent. Dark matter halos have to assemble faster than standard models predict. Every step in the process has to happen at the upper end of what is theoretically possible. And it has to happen not just in 1 or 2 rare cases, but in enough galaxies that Webb is finding them routinely. That has led to 3 broad categories of explanation, none of them entirely comfortable. The first is that our models of star formation in the early universe are incomplete. Maybe the first generation of stars, the ones formed from pure hydrogen and helium, were far more efficient at converting gas into stars than we assumed. In the modern universe, only about 10% of the gas in a galaxy ever becomes stars. The rest is either heated and blown out by supernova explosions and stellar winds, or it stays cold and diffuse, never collapsing. In the early universe, without heavy elements to help the gas cool and without as much dust to absorb radiation, star formation might have been much more aggressive. Some simulations suggest that under the right conditions, early galaxies could have converted 20 or 30% of their gas into stars in a single burst. That would give them a huge head start in building mass. The downside of this explanation is that it requires early galaxies to behave in ways we have never directly observed. We do not have a local analog. Every star-forming region we can study in detail is full of heavy elements and shaped by billions of years of prior stellar activity. Extrapolating backward to a universe with no metals and no history is guesswork informed by physics, but still guesswork. The second explanation is that dark matter itself behaved differently in the early universe. Most cosmological models assume that dark matter is cold, meaning it moves slowly and clumps together gradually over time. That assumption works well for explaining the large-scale structure we see today, but it might underestimate how quickly dark matter halos could form in the densest regions of the early universe. If dark matter clumped faster than standard cold dark matter models predict, galaxies would have had deeper gravitational wells to fall into, and that would accelerate everything downstream. Gas would fall in faster, stars would form faster, galaxies would grow faster. There is some theoretical wiggle room here. Alternatives to cold dark matter, like warm dark matter or self-interacting dark matter, predict slightly different clustering behavior, but none of those alternatives are mainstream, and most of them come with their own problems that make them hard to reconcile with other observations. Invoking a change in dark matter properties to explain early galaxies is not impossible, but it is a big move. It has consequences for everything else in cosmology, and so far no one has found a version of modified dark matter that solves the early galaxy problem without breaking something else. The third explanation, and the one that has been getting the most attention, is that many of these bright early galaxies are not glowing primarily because of stars. They are glowing because they contain supermassive black holes that are actively feeding. When a black hole pulls in gas, that gas heats up to millions of degrees and radiates enormous amounts of energy before it crosses the event horizon. A supermassive black hole in the process of eating can outshine an entire galaxy of stars. If some of the objects Webb is detecting are actually quasars or active galactic nuclei rather than normal star-forming galaxies, that would explain the brightness without requiring implausibly fast star formation. The problem is that supermassive black holes come with their own timeline issues. A black hole with 1 billion solar masses takes time to grow. If it starts from a single collapsed star, which weighs maybe 10 or 20 times the mass of the Sun, It has to double in mass many times over to reach 1 billion. Even if it feeds at the maximum rate allowed by physics, a limit called the Eddington rate, it takes hundreds of millions of years to get that large. Finding supermassive black holes in galaxies that are only 300 or 400 million years old pushes that growth timeline to its breaking point. Some researchers have proposed that the first black holes did not form from stars at all, they formed from direct collapse. In this scenario, massive clouds of primordial gas in the early universe skipped the star formation step entirely and collapsed straight into black holes weighing tens of thousands or even hundreds of thousands of solar masses. Starting with a seed that large gives the black hole enough time to grow to 1 billion solar masses within a few 100 million years. The idea is not new. It has been around for more than a decade, but it was considered speculative, a solution in search of a problem. Webb may have just handed it the problem. Spectroscopy is starting to sort out which galaxies are genuinely dominated by stars and which ones might be hiding black holes. Webb's instruments can identify emission lines from highly ionized gas, a signature of intense radiation fields like the ones produced by accreting black holes. In some of the early massive galaxies, those lines are present, in others they are not. That suggests the population is mixed. Some of these objects are genuinely star-forming galaxies that assembled faster than expected. Others are likely powered by black holes. Both categories are challenging for theory, just in different ways, and both are showing up more often than models predicted. The fact that Webb is finding so many of these objects is almost as troubling as the objects themselves. Rare events happen. Outliers exist. If Webb had found 1 or 2 massive galaxies in the first few 100 million years, astronomers could shrug and chalk it up to luck, a statistical fluke, the universe trying out something unusual in a corner we happen to point a telescope at. But Webb is not finding 1 or 2. It is finding dozens, maybe hundreds, depending on how you count. That suggests these galaxies are not freaks. They are a normal part of the early universe, which means our models are not just slightly off. They are missing something structural. That realization has led to a flurry of new research. Teams around the world are revisiting their simulations, tweaking parameters, testing alternative assumptions. Some are exploring whether the initial conditions of the universe, the tiny density fluctuations imprinted in the first fraction of a second after the Big Bang, were more extreme in certain regions than the standard model assumes. Others are investigating whether feedback from the first stars, the radiation and supernova explosions that heat and expel gas, was weaker in the early universe than it is today. A few groups are even questioning whether the cosmological parameters themselves, the numbers that describe the universe's expansion rate, its matter density, its dark energy content, might need slight adjustments. None of these ideas are radical enough to overturn the Big Bang model. The Big Bang is not in trouble. The broad outline, expansion from a hot, dense state, cooling over time, structure forming under gravity, is as solid as ever. What is in trouble is the detailed timeline, the when and the how fast, the specific sequence of events that took the universe from a smooth fog of hydrogen to a cosmos full of galaxies. Webb is showing us that the sequence happened faster than we thought. And the faster it happened, the harder it is to explain without invoking processes we do not fully understand or have not observed directly. One useful comparison is to think of the early universe as a construction site. The standard model gave us a blueprint. It told us how long each stage of construction should take: foundation first, then framing, then walls, then roof. But Webb has driven past the site and found buildings that are already finished. Roofs on, windows in, lights on inside. and the timeline says they should still be pouring the foundation. That does not mean the blueprint is completely wrong. It means something about the construction process is faster or more efficient than the blueprint assumed. Maybe the crews are bigger. Maybe the materials are different. Maybe there is a shortcut no one knew about. The job now is to figure out what that shortcut is and whether it applies to every building or just a few. Because if every galaxy in the early universe was assembling this fast, the implications ripple forward through the entire history of the cosmos. It changes when the first heavy elements appeared, when the first planets could have formed, when the first potentially habitable environments became possible. It compresses the timeline for everything that came after, including, theoretically, us. The narrative that has emerged in the popular press is that Webb is rewriting the textbooks. That phrase has been used so many times in the last 2 years that it has almost lost meaning. But in this case, it is not an exaggeration. Textbooks written 5 years ago described the early universe as a slow, gradual process. Textbooks written today will have to account for galaxies that formed in a fraction of that time. Lecture slides will be updated. Intro astronomy courses will teach a different timeline. PhD students who built their dissertations on models of early galaxy formation are going back to their simulations and starting over. This is not a crisis in the sense that cosmology is collapsing. It is a crisis in the sense that a major piece of the story was wrong, and fixing it is going to take years of work. The James Webb Space Telescope is not slowing down. It is still observing, still collecting data, still finding more of these galaxies, and every new detection adds another data point to the pile that theorists have to explain. Some of the explanations will work, others will not. Eventually, a new consensus will form, a revised model that accounts for what Webb is seeing. But that process takes time, and in the meantime, we are left with the uncomfortable truth that the universe in its infancy was stranger, faster, and more chaotic than we gave it credit for. The galaxies Webb is finding are not impossible, they are just unthinkable, which means we were not thinking hard enough, or we were thinking about the wrong things. Either way, the early universe has stopped cooperating with our expectations, and the deeper Webb looks, the more it becomes clear that the cosmos does not care what we expected. It did what it did, and now we have to catch up. What makes this especially unsettling is the realization that we are only seeing a tiny fraction of what is out there. Webb's deepest surveys cover areas of sky measured in square arc minutes. For context, the full moon is about 30 arc minutes across. Webb's largest survey to date, the one that found 800,000 galaxies, covered an area equivalent to about 3 full moons placed side by side. That is a vanishingly small piece of the sky. The entire sky, all the way around the Earth in every direction, covers about 41,000 square degrees. Webb has surveyed a fraction of a percent of that, and in that tiny slice it has found dozens of galaxies that challenge our models. Scale that up. If the same density of surprising early galaxies holds across the entire sky, there could be tens of thousands of them, maybe more, each one a puzzle, each one demanding an explanation. The sheer number implies that whatever process built these galaxies was not rare, it was common, maybe even dominant. That shifts the question from why do these galaxies exist to why did we ever think they would not? And that question does not have a comfortable answer, because the reason we thought they would not exist is that our models said so. The models were built on observations of the nearby universe, extrapolated backward using physics we understand. And they worked, right up until Webb started looking at the actual early universe and found that the models were missing something. What that something is, no one knows yet. But whatever it is, it was powerful enough to build galaxies faster than gravity alone should allow. and it left no obvious trace in the galaxies we see today, which means the early universe was not just a younger version of the universe we live in now. It was a different place, operating under conditions we can only glimpse through instruments like Webb. And every new image, every new spectrum, every new detection is pulling back the curtain a little further. What we are seeing behind that curtain is not comforting. It is a cosmos that assembled itself faster, more violently, and more efficiently than we predicted. A cosmos that does not wait. And beneath all of that, threaded through every galaxy, every star, every bit of glowing gas, is a structure so vast and so intricate that it makes the galaxies themselves look like scattered dots, a web, stretching across the entire universe, connecting everything to everything else, and Webb is starting to map it. The galaxies Webb is finding, scattered across the early universe, massive and bright and forming faster than they should, are not sitting there in isolation. They are not scattered randomly across empty space like coins tossed onto a table. They are organized, connected, threaded together by something so vast and so intricate that for most of human history we had no idea it was there. We looked at the night sky and saw stars. Then we looked closer and saw galaxies. Millions of them. Billions of them. Each one a self-contained island universe. But pull back far enough. Look at the full picture from a distance no human will ever reach. And the galaxies stop looking like islands. They start looking like neurons, nodes in a network, points of light connected by invisible strands stretching across hundreds of millions of light years. The universe is not a random spray of galaxies flung outward from the Big Bang. It is a web, a cosmic web, and everything, every galaxy, every star, every planet, every atom you are made of, sits somewhere inside it. This is not a metaphor. The cosmic web is a real physical structure, the largest structure in the universe. It is made of dark matter and gas, woven together by gravity over billions of years into a pattern so complex and so organized that it looks designed. It is not designed. It is the natural result of matter collapsing under its own weight in an expanding universe. But the first time you see it, the first time you look at a map of galaxy distribution across a large enough volume of space, your brain does not want to accept that it formed on its own. It looks too deliberate, too structured, too much like something built by intention rather than physics. The cosmic web is composed of filaments, sheets, knots, and voids. The filaments are long thread-like strands of dark matter and gas, stretching across tens or hundreds of millions of light years. They connect clusters of galaxies the way blood vessels connect organs. Galaxies do not just sit inside these filaments, they form along them. The filaments act as highways, funneling gas from the empty regions of space into the dense knots where galaxies ignite. The sheets are thinner, flatter structures, walls of galaxies stacked together like layers in a cake. The knots are where multiple filaments intersect, creating massive galaxy clusters containing hundreds or thousands of galaxies bound together by gravity, and the voids are the empty spaces between. Not empty in the sense of being a perfect vacuum, empty in the sense that there is almost nothing there, no galaxies, no stars, just a few stray atoms of hydrogen drifting through darkness across regions that can span hundreds of millions of light years. The voids are larger than the filaments, much larger. If you could somehow map the entire observable universe and color the regions based on density, the voids would dominate. Most of the volume of space is empty. The galaxies, the stars, the planets, all the matter we can see, all of it is compressed into the filaments and knots. The universe is not evenly distributed. It is clumpy, threaded, and the threads are where everything happens. We live inside one of those threads. The Milky Way sits in a region of space called the local sheet, a flat distribution of galaxies that stretches across a few 100 million light-years. We are not in a massive cluster. We are not in a dense knot. We are in a relatively quiet neighborhood on the edge of a filament that connects us to larger structures nearby. The closest big knot is the Virgo cluster, about 50 million light-years away. The Virgo cluster contains more than 1,000 galaxies, all bound together in a region about 15 million light-years across. Beyond Virgo is an even larger structure called the Laniakea supercluster, a collection of galaxy clusters and filaments spanning more than 500 million light-years. Laniakea contains about 100,000 galaxies. We are part of it. The Milky Way, Andromeda, the Virgo cluster, all of it sits inside this one supercluster. And Laniakea is just one of millions of superclusters scattered across the observable universe, each one connected to the next by filaments stretching across the cosmic web. The web itself formed over billions of years. In the first few 100,000 years after the Big Bang, matter was distributed almost uniformly. Almost. There were tiny fluctuations in density, regions where the matter was slightly more concentrated than average. Those fluctuations were imprinted in the early universe by quantum effects during the inflationary period, the brief moment right after the Big Bang when space expanded faster than light. As the universe expanded and cooled, gravity went to work on those fluctuations. The denser regions pulled in more matter. The less dense regions lost matter. Over millions of years, the contrast grew. The dense regions became denser. The voids became emptier. Dark matter, which makes up most of the matter in the universe, led the way. It does not interact with light or normal matter except through gravity, so it was free to collapse into clumps without being slowed by radiation or pressure. Normal matter, the hydrogen and helium that would eventually form stars, followed the dark matter. It fell into the gravitational wells created by dark matter halos and began to cool and condense. As those halos grew and merged, they formed larger and larger structures. Small clumps became filaments. Filaments connected to form sheets. Sheets intersected to create knots. And the voids in between expanded as matter drained out of them and into the denser regions. The result is the pattern we see today, a universe that looks, from a distance, like a neural network, or a sponge, or a foam. Pick your analogy. The point is the same. The universe has structure on the largest scales, and that structure is not random. The cosmic web was predicted before it was observed. In the 1970s and 80s, computer simulations of structure formation in the universe began to show that matter should naturally organize itself into filaments and voids. The simulations started with a smooth distribution of dark matter, applied the laws of gravity, and let the system evolve over billions of simulated years. The result, every time, was a web. The details varied depending on the initial conditions and the cosmological parameters used, but the overall pattern was always the same. Filaments, sheets, knots, voids. The predictions were clear. The challenge was confirming them. Mapping the three-dimensional distribution of galaxies across a large enough volume of space to see the web requires enormous surveys. You need to measure the distances to millions of galaxies. You need to cover a significant fraction of the sky, and you need to look deep enough to capture the structure at different epochs in cosmic history. That kind of survey was not possible until the late 20th century. Early galaxy catalogues were small and shallow. They showed clustering, hints that galaxies were not distributed randomly, but they did not have the coverage or the depth to reveal the full web. Then in the 1990s, a project called the Sloan Digital Sky Survey began operations. The Sloan Digital Sky Survey, usually just called SDSS, is one of the most ambitious astronomical projects ever undertaken. It uses a dedicated telescope in New Mexico to map the positions and distances of millions of galaxies and stars across more than a third of the sky. The survey measures redshifts, the stretching of light caused by the expansion of the universe, to determine how far away each galaxy is. By combining position and distance, astronomers can build a three-dimensional map of where galaxies are located in space. The first data release from JWST came in the early 2000s, and it confirmed what the simulations had predicted. The galaxies were not scattered randomly, they were organized into filaments and walls. The voids were real, enormous empty regions where almost no galaxies existed. And the filaments connected everything, stretching across hundreds of millions of light-years in continuous threads. The structure was undeniable. The cosmic web was not a theory anymore. It was an observation. And the maps were stunning. If you plot the galaxies from JWST in 3 dimensions and rotate the view, the web becomes obvious. You can see the filaments stretching outward from our position. You can see the voids, dark gaps where nothing exists. You can see the clusters, bright, dense knots where thousands of galaxies pile up. It looks organic, it looks planned, and it is neither. It is just gravity doing what gravity does, pulling matter together, creating structure, building the scaffolding on which galaxies hang. The cosmic web is not static, it is evolving. Matter is still flowing from the voids into the filaments. Filaments are still feeding gas into galaxy clusters. Clusters are still growing as smaller galaxies fall into them. The web is dynamic, a living structure constantly reshaping itself on timescales of billions of years, and the James Webb Space Telescope has started to map it in the early universe. One of Webb's most surprising discoveries came in June 2024, when a team of astronomers published observations of a 3 million light-year-long filament containing 10 ancient galaxies and a supermassive black hole, seen as it existed only 830 million years after the Big Bang. 3 million light-years. That is farther than the distance from the Milky Way to Andromeda. And this filament, this thread of galaxies connected by dark matter and gas, was already in place when the universe was less than 1 billion years old. The discovery was surprising because the standard model predicted that the cosmic web would take longer to assemble. Filaments should be small and faint in the early universe, gradually growing larger as matter accumulates over billions of years. But this filament was not small, it was not faint, it was massive and clearly defined, stretching across millions of light-years with galaxies already forming along its length. The structure was there, fully formed, far earlier than expected. Then in late 2024, Webb found something even more striking. A cosmic vine, a filament 13 million light-years long and 650,000 light-years wide, containing a mass equivalent to 260 billion suns. The structure was identified in a region of sky called the Extended Growth Strip, located in the constellation Ursa Major. The filament was observed as it existed in the early universe, and it was already dense with galaxies. The sheer size of it caught astronomers off guard. Xiaohui Fan, an astronomer at the University of Arizona and one of the researchers who studied the structure, said plainly that he was surprised by how long and how narrow the filament was. He did not expect such a long, distinctly thin structure to exist that early. The cosmic vine is predicted to eventually evolve into a massive galaxy cluster, something comparable to the Coma cluster, one of the largest and densest clusters in the nearby universe. But at the time Webb observed it, the vine was still in the process of pulling itself together. Galaxies were forming along the filament, feeding off the gas funneled in by gravity. And at the densest points, where the filament knotted, supermassive black holes were already active, pulling in matter and radiating enormous amounts of energy. The filament was a factory, a pipeline, a highway for gas and dark matter moving from the voids into the regions where galaxies could form. What makes these discoveries significant is not just that the filaments exist, it is that they exist so early. The cosmic web was supposed to take billions of years to develop its full structure. Webb is finding filaments, massive and well-defined, in the first billion years. That means the process of structure formation was faster in the early universe than models predicted. The same problem that is showing up in the galaxies themselves, the fact that they are too massive and too mature for their age, is also showing up in the web. The scaffolding assembled faster than it should have. The threads were already in place when the universe was still a toddler. And that raises the same uncomfortable questions. What process allowed the cosmic web to form so quickly? Was dark matter clumping faster than we thought? Was the initial distribution of matter less smooth than we assumed? Was there some additional force or mechanism in the early universe that accelerated structure formation? No one knows. But the evidence is piling up that something about the early universe was different, more efficient, more aggressive. The cosmos did not wait. It built the web fast, and galaxies followed. The role of supermassive black holes in shaping the cosmic web is another piece of the puzzle. Black holes do not just sit passively at the centers of galaxies. When they are actively feeding, when they are pulling in gas and dust and growing, they release enormous amounts of energy. That energy comes out in the form of radiation and powerful jets of particles that can travel at near light speed. Those jets and the radiation create what astronomers call cosmic winds, winds that blow gas out of galaxies and into the surrounding space. In some cases, those winds are strong enough to fling matter across millions of light years from one part of a filament to another. The black holes act as pumps, redistributing gas along the web. They pull matter in through gravity, heat it to millions of degrees, and then blast it back out into the filament. The gas cools, condenses, and eventually falls back into another galaxy down the line. The process sculpts the filaments. It regulates how much gas is available for star formation. And it ties the evolution of galaxies to the evolution of the web itself. A galaxy sitting in a dense part of a filament has access to more gas. It can form stars faster. It can grow more massive. A galaxy sitting in a void has almost no gas to work with. It forms stars slowly, if at all, and eventually runs out of fuel. The web determines the fate of galaxies. And the galaxies, through their black holes and their star formation, shape the web in return. It is a feedback loop, a conversation between matter and gravity that has been running for more than 13 billion years. The voids, the empty spaces between the filaments, are harder to study because there is almost nothing in them, but they matter. They are not irrelevant gaps. They are part of the structure. The voids are where matter used to be. Early in the universe, the regions that are now voids contained gas and dark matter, just like everywhere else. But as structure began to form, gravity pulled that matter out of the less dense regions and into the filaments. The voids expanded as the universe expanded, but the matter inside them did not keep up. It drained away, leaving behind vast stretches of space where almost no galaxies exist. Some voids are hundreds of millions of light years across. If you were somehow standing in the middle of one, looking out in every direction, you would see almost nothing. No stars, no galaxies, just darkness. The nearest galaxy might be 50 million light years away. The nearest cluster might be 100 million. You would be more isolated than any human has ever been, surrounded by emptiness on a scale that makes the space between stars look crowded. The voids are not completely empty. There are a few dwarf galaxies scattered through them, a few stray atoms of hydrogen, but compared to the filaments they are deserts, and they are growing. As the universe expands, the voids expand faster than the filaments because there is less matter in them to resist the expansion. The web is stretching, the threads are getting longer, the voids are getting larger, and eventually, billions of years from now, the expansion will reach a point where the filaments themselves begin to tear apart. Galaxies will drift out of reach of each other, the web will dissolve, and the universe will become a much lonelier place. For now, the web holds. Gravity is still strong enough to keep the filaments intact. Matter is still flowing from the voids into the dense regions. Galaxies are still forming, still evolving, still lighting up the threads. And the James Webb Space Telescope is mapping it all. Not the entire web, that would take thousands of years, but pieces of it, slices, snapshots of what the web looked like at different points in time. By combining observations of the nearby universe with observations of the early universe, astronomers can trace how the web has evolved. They can see which filaments have grown thicker, which clusters have merged, which voids have expanded. The story of the universe is written in the structure of the web. And the more we learn about that structure, the more it becomes clear that the web is not just the background, it is the story. The web is why galaxies formed where they did. It is why some galaxies are massive and others are small. It is why clusters exist. It is why voids exist. The web is the skeleton of the universe. Everything else is built on top of it. The comparison to a neural network is more than just a visual similarity. Simulations of the cosmic web and simulations of neural networks in the brain show similar branching patterns, similar distributions of nodes and connections, similar statistical properties. Some researchers have started asking whether the resemblance is coincidental or whether there is some deeper principle at work, some common rule that governs how complex systems organize themselves at vastly different scales. That is still speculation. There is no theory that connects the two. But the fact that the question is even being asked tells you how strange the cosmic web looks. It is a structure that feels intentional, and yet it is entirely the result of dumb physics. Gravity pulling on matter, matter collapsing into the lowest energy state. No plan, no designer, just time and force, and the initial conditions set by the Big Bang. That something so intricate, so organized, can emerge from such simple rules is one of the most profound facts about the universe. Complexity does not require intelligence. It just requires time and the right starting conditions. The cosmic web is proof of that. And it is beautiful and terrifying. Beautiful because it reveals an order underlying the chaos. Terrifying because it shows us how small we are, how isolated. The Milky Way is one galaxy in one filament in one supercluster in a web containing 2 trillion galaxies. We are a single point in a structure so large that light takes tens of billions of years to cross it. And most of that structure, most of those 2 trillion galaxies, we will never reach. We will never visit. We will never even see directly. The web connects us to everything in principle. But in practice, the distances are too great, the expansion too fast. We are trapped in our corner of the web, watching, mapping, trying to understand how it all fits together, and beneath it all, woven through every filament, every galaxy, every atom, is something we still do not understand, something that is not matter, not dark matter, not light, something that is pulling the web apart, stretching the voids, accelerating the expansion, a force with no name and no explanation, pushing everything away from everything else. And the faster the universe expands, the harder it becomes to hold the web together. Gravity is fighting, but it is losing. And what is winning is invisible. The invisible hand, dark energy's relentless grip. Gravity is fighting a war it cannot win. For billions of years it has been the dominant force in the universe, pulling matter together, building galaxies, holding stars in their orbits, keeping clusters bound. Gravity shaped the cosmic web. It sculpted the filaments. It created the structure we have been mapping. And all the while, quietly, invisibly, something else has been working against it. Not fighting gravity directly, not cancelling it out, just slowly, steadily, relentlessly pushing everything apart, stretching the space between galaxies, widening the voids, accelerating the expansion of the universe itself. And gravity, for all its power, for all the billions of years it spent assembling the cosmos, is losing. The thing that is winning has a name. We call it dark energy, but that name is a placeholder, a label we stuck on a phenomenon we do not understand. Dark energy is not dark the way dark matter is dark. Dark matter is invisible because it does not interact with light, but it is still matter. It has mass. It clumps together under gravity. It builds halos. We can map it by watching how it bends light and affects the motion of galaxies. Dark energy is something else entirely. It is not matter. It is not a particle. It is not made of atoms or fields or anything we have ever directly observed. It is a property of space itself, and it is everywhere, in the gaps between galaxies, in the voids, in the room you are sitting in right now, between the atoms in your body. It is woven into the fabric of the universe at the most fundamental level, and it is pulling everything apart. We did not discover dark energy by looking for it. We discovered it by accident, the way most of the most important discoveries in science happen. In the late 1990s, two independent teams of astronomers were studying distant supernovae, trying to measure how fast the universe was expanding at different points in its history. The expectation was straightforward. The universe had been expanding since the Big Bang. Gravity had been pulling on that expansion, slowing it down, the way friction slows a car after you take your foot off the gas. The question was how much the expansion had slowed. Was it decelerating fast enough that the universe would eventually stop expanding and collapse back in on itself in a big crunch? Or was it slowing gradually, destined to keep expanding forever but at an ever-decreasing rate? Those were the two options on the table, slow collapse or slow drift. Both seemed reasonable, both fit the basic physics. The teams were not expecting a third option. They were not expecting the universe to be speeding up. To measure how the expansion rate has changed over time, you need a kind of cosmic yardstick, something bright enough to be seen across billions of light years, something with a known brightness, so you can calculate how far away it is by measuring how dim it looks from Earth. The teams used a specific type of exploding star called a Type 1a supernova. These supernovae form when a white dwarf, the dense leftover core of a dead star, pulls matter off a companion star until it reaches a critical mass. At that point, the white dwarf detonates in a thermonuclear explosion. The explosion is so consistent, so predictable in its peak brightness, that astronomers can use it as a standard candle. Spot a Type 1a supernova in a distant galaxy, measure how bright it looks, compare that to how bright it should be, and you have the distance. Measure the galaxy's redshift, which tells you how fast it is moving away, and you have the expansion rate at the time the supernova exploded. Do that for dozens of supernovae at different distances, which is the same as saying different points in time, and you can map how the expansion has changed over billions of years. Both teams, one led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the other led by Brian Schmidt and Adam Rees working with the High-Z Supernova Search Team, spent years collecting data. They observed supernovae in galaxies billions of light-years away, they measured distances, they measured redshifts, they built models, and when they finally analyzed the results, both teams found the same thing. The distant supernovae were dimmer than expected, not by a lot, not by an amount that screamed error, but by enough that it could not be ignored. Dimmer meant farther. Farther meant the universe had expanded more than the models predicted. The expansion was not slowing down, it was speeding up. The universe was accelerating. At first, both teams assumed they had made a mistake. Perlmutter's group checked their data again and again, looking for systematic errors, dust that might be dimming the light, calibration issues with their instruments. Schmidt's team did the same. Both groups came to the same conclusion independently. The data was solid. The supernovae were dimmer because the universe really had expanded more than it should have if gravity was the only force at play. The announcement came in 1998. Two papers published within months of each other, both reporting the same result. The universe was not just expanding, it was accelerating. And no one had any idea why. The discovery was so unexpected, so contradictory to the prevailing understanding of cosmology, that it took years for the community to fully accept it. But the evidence kept piling up. More supernovae, better measurements, independent confirmation from other methods. By the early 2000s, the accelerating expansion was no longer controversial. It was a fact. And in 2011, Perlmutter, Schmidt and Rees were awarded the Nobel Prize in Physics for the discovery. The problem was that acceleration requires a cause. In physics, nothing accelerates without a force pushing on it. If the universe is speeding up, something has to be doing the pushing. Gravity pulls, it does not push. So whatever this force was, it could not be gravity. It had to be something else. Something that acts opposite to gravity. Something that becomes stronger, not weaker, as space expands. The term that stuck was dark energy, not because it is dark, not because it is energy in the way we usually think of energy, but because we have no idea what it is and we needed a name. Dark energy is the label we put on the unknown cause of cosmic acceleration. It is a confession of ignorance wrapped in a two-word phrase. The simplest explanation, and the one that fits the data best, is that dark energy is a cosmological constant. The cosmological constant, usually written with the Greek letter lambda, is a term that can be added to Einstein's equations of general relativity. Einstein originally introduced it in 1917 as a way to keep the universe static. At the time, he believed the universe was eternal and unchanging, but his equations predicted that the universe should either be expanding or contracting. To force the equations to allow a static universe, he added a constant term representing a kind of energy inherent to empty space itself, a repulsive force that could balance gravity and hold everything in place. Then, in 1929, Edwin Hubble discovered that the universe was expanding. Einstein realized his static universe was wrong and reportedly called the cosmological constant his biggest blunder. For decades, physicists assumed the constant was zero, that empty space had no energy, that the universe was just matter and gravity and expansion left over from the Big Bang. Then the supernova teams found acceleration, and the cosmological constant came back from the dead. If empty space has energy, and that energy does not dilute as the universe expands, then it acts like a repulsive force. The more space you have, the more dark energy you have. As the universe expands, the amount of dark energy grows. Matter and gravity get weaker because they spread out. Dark energy gets stronger because it is tied to the volume of space itself. Eventually, dark energy wins. Gravity loses its grip, and the expansion accelerates. The cosmological constant is not the only possible explanation. There are alternatives. One is called quintessence, a hypothetical field that fills space and changes over time, unlike the constant which stays fixed. Quintessence could be stronger in the past and weaker now, or vice versa. It could evolve depending on the state of the universe. Another option is modified gravity, the idea that Einstein's equations are incomplete and that gravity behaves differently on the largest scales. Maybe the universe is not accelerating at all. Maybe what looks like acceleration is actually a sign that our understanding of gravity breaks down when applied to the entire cosmos. A third possibility is that the acceleration is an illusion caused by the way matter is distributed. The universe is not smooth, it is clumpy. Some regions are denser than others. The expansion rate might vary from place to place, and what we measure as an average might not reflect what is actually happening everywhere. This idea is called back reaction, and it is controversial. Most cosmologists think the effect is too small to explain the observed acceleration, but it is still on the table. None of these alternatives have gained as much traction as the cosmological constant. The simplest model, where dark energy is constant in time and uniform in space, fits the data better than anything else. That does not mean it is right, it just means it works, for now. Quantifying dark energy is tricky because it is not a force in the traditional sense. It does not push on objects the way a wind pushes on a sail. It affects the expansion of space itself. The way astronomers describe it is in terms of how much the expansion rate changes with distance. For every megaparsec of distance, about 3.26 million light-years, the recession speed of a galaxy increases by roughly 70 kilometers per second due to the expansion of space. That number, called the Hubble constant, includes the effects of both matter and dark energy. The contribution from dark energy specifically is harder to isolate, but recent estimates put it at around 46 miles per second per megaparsec. That might not sound like much. 46 miles per hour is slower than highway traffic, but it compounds. For every additional megaparsec you look, the effect adds another 46 miles per second. At 10 megaparsecs, it is 460 miles per second. At 100 megaparsecs, it is 4,600 miles per second. At 1 billion megaparsecs, galaxies are receding at speeds far exceeding the speed of light, not because they are moving through space faster than light, which is impossible, but because the space between us and them is expanding faster than light can cross it. That is what dark energy does. It stretches space, and the farther you look, the faster things appear to move away. The most unsettling part of dark energy is not what it is doing now, it is what it will do in the future. The universe is currently about 13.8 billion years old. For most of that time, matter and gravity were in control. Dark energy was present but weak. The universe was denser. Galaxies were closer together. Gravity dominated. But as the universe expanded, the density of matter dropped. Galaxies spread out. The gravitational pull between them weakened. Dark energy, tied to the volume of space, stayed constant or possibly even grew stronger. About 5 or 6 billion years ago, dark energy crossed a threshold. It became stronger than gravity on the largest scales. That is when the acceleration began, and it has been acceleration ever since. The current models, based on a cosmological constant, predict that dark energy will continue to dominate indefinitely. The expansion will keep speeding up. Galaxy clusters will drift farther apart. The filaments of the cosmic web will stretch. The voids will grow. Eventually, billions of years from now, galaxies outside our local group will recede so fast that their light will never reach us. The observable universe will shrink, not because space itself is shrinking, because the edges of what we can see will be defined by how far light can travel in an accelerating cosmos. Galaxies that are visible today will vanish from view. One by one, the distant galaxies will redshift into invisibility. The sky will go dark, not because the galaxies have died, because the space between us and them is expanding too fast for their light to bridge the gap. This scenario is called the heat death or big freeze. It is the most likely fate of the universe under current models. Trillions of years from now, the only galaxies left in view will be the ones gravitationally bound to the Milky Way, Andromeda, the local group. A few dozen galaxies clustered together, their mutual gravity strong enough to resist the expansion. Everything else will be gone. The cosmic web will have torn apart, the filaments will have dissolved. The universe will be cold, dark, and empty except for the small island of galaxies we are part of. Star formation will slow as galaxies run out of gas. Stars will age and die. Black holes will evaporate over timescales so long that calling them billions of years is laughable. Eventually, even the black holes will vanish, and all that will be left is a thin soup of particles spreading through an ever-expanding void. That is the heat death. Not a dramatic explosion, not a sudden end, just a slow, quiet fade into darkness. There is another possibility, a more dramatic one. If dark energy is not constant, if it is instead a field that can grow stronger over time, the expansion could accelerate so much that it eventually tears apart everything, not just galaxy clusters, not just galaxies, everything. This scenario is called the Big Rip. In a Big Rip scenario, dark energy increases without limit. As it grows stronger, it overcomes not just gravity on cosmic scales, but gravity on smaller scales too. First, galaxy clusters unbind, then individual galaxies shred as the space between stars expands faster than their gravity can hold them together. Then solar systems dissolve, planets drift away from their suns. Eventually, even the atomic forces holding matter together give way. Atoms are ripped apart. Protons and neutrons disintegrate. The universe ends not in darkness, but in total disintegration, everything torn to pieces by runaway expansion. The Big Rip is not the favored scenario. Most cosmologists think dark energy is constant or close to constant, but the possibility cannot be ruled out completely. If the models are wrong, if dark energy is dynamic and growing, the Big Rip could happen in as little as 20 billion years, or it could be trillions of years away, or it could never happen at all. The uncertainty is the point. We do not know what dark energy is. We do not know how it behaves over time. We are watching the universe accelerate and trying to extrapolate forward with equations that might be missing something fundamental. The James Webb Space Telescope cannot directly detect dark energy. Dark energy does not emit light. It does not absorb light. It does not interact with matter in any way we can measure, except through its effect on the expansion of the universe. Webb is not designed to measure expansion rates directly. That job belongs to other instruments, ground-based telescopes, other space missions, surveys that map the distances and redshifts of millions of galaxies across the sky. But Webb is contributing to the conversation indirectly. By observing the early universe, by mapping how galaxies formed and evolved, Webb is helping astronomers test whether the standard cosmological model, the one that includes dark energy as a cosmological constant, is correct. And the early results are making that question more complicated. The massive galaxies Webb has found in the first few 100 million years after the Big Bang do not fit easily into the standard model. The cosmic web assembling faster than expected does not fit. The supermassive black holes appearing earlier than they should does not fit. None of this directly contradicts dark energy, but it suggests that the timeline of the universe, the sequence of events from the Big Bang to now, might be different than we thought. And if the timeline is different, the expansion history might be different. And if the expansion history is different, the properties of dark energy might need to be revised. In 2024, Adam Rees, one of the original discoverers of dark energy and a researcher at Johns Hopkins University, published a statement based on new data from Webb and Hubble. He said that new observations suggest a new feature in the universe, not a flaw in telescope measurements, may be behind why the universe is expanding faster today than it did in its infancy. That phrase, a new feature in the universe, is careful. It does not say what the feature is. It does not claim dark energy is changing. It just acknowledges that something about the universe does not match the simplest models. Whether that something is dark energy itself evolving over time or some other factor we have not accounted for is still an open question. The tension between different measurements of the expansion rate, the same tension that has been growing for the last decade, has not gone away. Some measurements using the cosmic microwave background give one answer. Other measurements using supernovae and galaxies give a different answer. The gap is small but persistent, and Webb's observations of the early universe are adding fuel to the argument on both sides. Some researchers think Webb's data supports the idea that dark energy is not perfectly constant. Others think the discrepancies point to problems with how we measure distances, not with dark energy itself. The debate is ongoing and loud. What is not debatable is that dark energy, whatever it is, makes up about 68 to 70% of the total energy content of the universe. Not 68% of the matter, 68% of everything. Matter, both normal and dark, accounts for the rest. Ordinary matter, the stuff that makes up stars and planets and people, is only about 5%. The universe is not mostly matter, it is mostly something else. Something we cannot see, cannot touch, and do not understand, and that something is in control. It is dictating how fast the universe expands. It is determining the ultimate fate of every galaxy, every star, every planet. Gravity built the universe. Dark energy is tearing it apart, slowly, gently, relentlessly, and there is nothing we can do to stop it. No force we can invoke to slow the expansion, no mechanism we can imagine that would reverse it. The cosmological constant, if that is what dark energy is, does not change. It does not weaken. It just keeps pushing forever. The philosophical weight of that is hard to overstate. For most of human history, we assumed the universe was stable, eternal, unchanging. Then we learnt it was expanding. That was unsettling enough, but at least expansion implied a history, a beginning, a big bang, a story. Acceleration changes the story. It gives the universe an ending, not a dramatic collapse back into a singularity, not a cyclical rebirth, just an end, a quiet dispersal into cold, empty space. The heat death is not a death in the sense of destruction, it is a death in the sense of cessation. The universe will still exist, it will just stop doing anything interesting. No new stars, no new galaxies, no new structures, just the remnants of what once was, drifting farther and farther apart until even light cannot connect them. That is the future dark energy is writing, and we are living in the brief window of cosmic history where the universe is still interesting, still full of galaxies and stars and planets, still capable of producing complexity, still capable of producing life. In a few trillion years that window will close. And any civilization that exists then will look out at a sky that contains only the galaxies in their immediate vicinity. Everything else will have vanished beyond the horizon. They will have no way to know that the universe was once larger, once full, once connected. They will think their local cluster is the entire universe, and they will be wrong. But they will have no way to prove it. The evidence will have accelerated beyond reach. That is what makes dark energy terrifying. Not that it will destroy us, we will be long gone before it becomes a problem for the Milky Way, but that it reveals a universe that is not built to last. The cosmic web, the galaxies, the stars, all of it is temporary. A brief flicker of order in a cosmos that is being pulled apart by forces we do not understand. Gravity gave us structure, dark energy is taking it away, and woven through all of that, invisible and untouchable, is something even stranger, something that makes up most of the matter in the universe but has never been directly observed, something that built the scaffolding galaxies hang on, something we call dark matter. And if dark energy is the force tearing the universe apart, dark matter is the glue that barely holds it together, the unreachable 94%. Dark matter and the veil of the unknown gravity is fighting a war it cannot win, and dark energy is the force pushing everything apart. But dark energy is not the only invisible hand shaping the universe. There is another, something older, something quieter. Something that does not push or pull in the way we usually think of forces. It just sits there, woven through the fabric of space, holding galaxies together while revealing almost nothing about itself. We call it dark matter, and it makes up roughly 27% of everything that exists. Add dark energy at 68% and you get 95%. Round down slightly to account for measurement uncertainty, and you land on 94%. 94% of the universe is made of things we cannot see, cannot touch, cannot measure directly, and do not understand. The remaining 4 to 5%, the sliver of existence that includes every star, every planet, every atom in your body, every photon of light that has ever reached a telescope, all of it is a rounding error. We are living in the leftovers. The visible universe, the one we spend our entire lives interacting with, the one we photograph and catalogue and study, is the minority component of reality. And the majority, the dark sector, is beyond our reach. Not beyond our reach in the sense that we lack the technology to study it yet. Beyond our reach in the sense that it does not interact with light. It does not emit radiation. It does not absorb photons. It does not block our view. It just exists, invisible, undetectable, except through the one thing it cannot hide: gravity. Dark matter was not discovered by looking for it. It was discovered by noticing that the universe was not behaving the way it should if only visible matter existed. The first hint came in the 1930s when a Swiss astronomer named Fritz Zwicky was studying a massive galaxy cluster called the Coma cluster. The cluster contains more than 1,000 galaxies, all bound together by gravity, orbiting a common center of mass. Zwicky measured how fast the galaxies were moving. Then he calculated how much mass the cluster would need to have to keep those galaxies from flying apart. The galaxies were moving too fast, far too fast. The visible matter in the cluster, all the stars and gas he could see, added up to only a fraction of the mass needed to hold everything together. Zwicky proposed that the cluster must contain a large amount of unseen matter. He called it dark matter. No one believed him. The idea was too strange, too speculative. Astronomers assumed Zwicky had made a mistake, or that there was some other explanation. For decades, the observation sat on a shelf, ignored. Then in the 1970s, an American astronomer named Vera Rubin started measuring the rotation curves of spiral galaxies. A rotation curve is a graph that shows how fast stars and gas are orbiting at different distances from the center of a galaxy. If most of a galaxy's mass is concentrated in the center, where the visible stars are brightest, then the outer regions should rotate more slowly. The farther out you go, the weaker the gravitational pull and the slower the orbit. That is how the solar system works. Mercury orbits the Sun faster than Earth. Earth orbits faster than Mars. The outer planets crawl. The math is straightforward. Rubin expected galaxies to behave the same way. They did not. She found that stars in the outer regions of galaxies were orbiting just as fast as stars closer to the center. In some cases, they were orbiting faster. The rotation curves were flat, not dropping off the way they should if visible matter was all there was. The only way to explain flat rotation curves was to assume that galaxies contain far more mass than we can see, and that mass has to be distributed differently than the visible matter. It cannot be concentrated in the center. It has to extend far beyond the visible disk, forming a halo that wraps around the entire galaxy. Rubin's observations were meticulous, her data was clean, and the conclusion was unavoidable. Galaxies are embedded in massive halos of invisible matter, dark matter. This time, the evidence was too strong to ignore. By the 1980s, dark matter had gone from a fringe idea to the foundation of modern cosmology. The next piece of evidence came from gravitational lensing. Einstein's general relativity predicts that mass bends space, and when space bends, light traveling through it follows the curve. If you look at a distant galaxy through a massive object like a galaxy cluster, the light from the distant galaxy gets distorted. Sometimes it stretches into arcs, sometimes it splits into multiple images, sometimes it just brightens and magnifies. By measuring how much the light bends, you can calculate how much mass is doing the bending. And when astronomers did that calculation for galaxy clusters, they found the same problem Zwicky had found in the 1930s. The visible matter was not enough, not even close. The lensing required far more mass than the stars and gas could account for. The only explanation was dark matter. Lots of it. Gravitational lensing does not just confirm that dark matter exists, it allows astronomers to map it. By analyzing how light from thousands of background galaxies is distorted as it passes through a foreground cluster, researchers can reconstruct the distribution of mass in the cluster. They can see where the dark matter is concentrated, where it is spread thin, how it clumps. The result is a map. Not a map of stars or gas, a map of invisible matter inferred entirely from how it bends light. It is like watching wind. You cannot see wind, but you can see trees bending, leaves moving, branches swaying. From the motion of the visible objects, you infer the presence of the invisible force. Dark matter is the same. We cannot see it, but we can see its effects on everything around it. The cosmic microwave background, the faint afterglow of the Big Bang, provided the third major line of evidence. The CMB is a snapshot of the universe when it was only 380,000 years old. At that point, the universe had cooled enough for hydrogen atoms to form, and photons stopped scattering off free electrons. The light that was released at that moment has been traveling through space ever since, stretched by the expansion of the universe into microwave wavelengths. The CMB is not perfectly smooth. It has tiny fluctuations in temperature, variations of only a few millionths of a degree. Those fluctuations represent density differences in the early universe, regions that were slightly denser than average, regions that were slightly less dense. Gravity has been working on those differences ever since, pulling matter into the denser regions and leaving the less dense regions emptier. Over billions of years, those tiny seeds grew into the cosmic web, the galaxies, the clusters, the voids. The pattern of fluctuations in the CMB tells us what the universe was made of when it was young. And the pattern does not match what you would expect from a universe containing only normal matter. Normal matter interacts with light. It can be pushed around by radiation. Dark matter does not interact with light. It is immune to radiation pressure. It can clump together earlier and more efficiently than normal matter. When physicists ran simulations of structure formation using only normal matter, the resulting patterns did not match the CMB. When they added dark matter, the match was nearly perfect. The CMB requires dark matter. Without it, the universe we see today could not have formed. So what is dark matter? The short answer is we do not know. The longer answer is that we have a list of possibilities, none of them confirmed. For decades, the leading candidate was something called WIMPs, weakly interacting massive particles. The name describes the properties these particles would need to have. Massive, meaning they have significant mass, enough to account for the missing matter in galaxies. Weakly interacting, meaning they do not interact with normal matter, except through gravity and possibly the weak nuclear force, one of the four fundamental forces in physics. WIMPs are appealing because they fit naturally into certain theories of particle physics. They could be stable, meaning they do not decay over time. They could have been produced in large quantities in the early universe, and they could still be around today, drifting through space, passing through planets and stars and your body without interacting with anything. Dozens of experiments have been built to detect WIMPs, sensitive detectors buried deep underground to shield them from cosmic rays. Tanks of liquid xenon or germanium crystals cooled to near absolute zero, waiting for the faint signal of a WIMP colliding with a nucleus. So far, none of them have found anything. WIMPs remain hypothetical. Another candidate is axions. Axions are much lighter than WIMPs, possibly 1 billion times lighter than a proton. They were originally proposed to solve a problem in particle physics unrelated to dark matter. But it turns out that if axions exist, they could be produced in enormous numbers in the early universe, enough to account for the missing mass. Axions would interact even more weakly than WIMPs. Detecting them would require different experiments, one sensitive to the extremely faint electromagnetic signals axions might produce when passing through strong magnetic fields. Those experiments are underway. No confirmed detection yet. A third option is primordial black holes, not the black holes that form from collapsing stars. Primordial black holes that could have formed in the chaotic first moments after the Big Bang, when density fluctuations might have been extreme enough to collapse directly into black holes without going through a stellar phase. These black holes could range in mass from tiny, smaller than an atom, to tens of times the mass of the Sun. If enough of them formed and survived, they could account for some or all of the dark matter. The problem is that primordial black holes should produce observable effects. They should occasionally pass through the solar system, tugging on planets. They should lens background stars when they drift in front of them. Surveys looking for these effects have found some candidates, but not nearly enough to explain all the dark matter. Primordial black holes might contribute to the total, but they are unlikely to be the whole story. There are other ideas: sterile neutrinos, self-interacting dark matter, fuzzy dark matter, dark photons. Each one comes with its own set of predictions and its own set of experiments designed to test those predictions, and each one, so far, has come up empty. Dark matter is real, the evidence for it is overwhelming, but we have no idea what it is made of. We cannot produce it in a lab. We cannot capture it. We cannot study it directly. All we can do is watch how it affects the things we can see and try to infer its properties from those effects. That is an incredibly frustrating position to be in. Imagine trying to understand water by only observing the ripples on its surface. You could learn a lot. You could figure out that something is there, that it has mass, that it responds to forces, but you would never know it is made of molecules. You would never know it is wet. You would never be able to hold it in your hand. That is where we are with dark matter. We can map it. We can measure its gravity. We can watch how it shapes galaxies and clusters, but we cannot touch it, and we might never be able to. The James Webb Space Telescope is contributing to this effort in a way that does not involve detecting dark matter particles directly. Webb cannot do that. No telescope can. But what Webb can do is map the distribution of dark matter across large regions of space using gravitational lensing. One of its major surveys, the Webb program, observed a region of sky for about 255 hours and identified nearly 800,000 galaxies. By analyzing how the light from those galaxies was distorted as it passed through foreground structures, researchers built a dark matter map, not a map of the galaxies themselves, a map of the invisible scaffolding the galaxies are sitting on. The map is the largest and sharpest dark matter map ever produced. It contains about 10 times more galaxies than ground-based maps of the same area and about twice as many as Hubble managed to capture. The resolution is extraordinary. Diana Scognamiglio, a researcher at NASA's Jet Propulsion Laboratory and the University of California, Riverside, who worked on the map, said plainly that this is the largest dark matter map we have made with Webb, and it is twice as sharp as any dark matter map made by other observatories. She added that now we are seeing the invisible scaffolding of the universe in stunning detail, thanks to Webb's incredible resolution. The map reveals something astronomers have suspected for years but could not confirm with this level of detail. Dark matter and normal matter are intertwined. They co-evolved. The dark matter clumped first, forming halos that pulled in gas. The gas cooled and condensed and eventually formed stars. Those stars assembled into galaxies. The galaxies followed the dark matter. Where dark matter is dense, galaxies are dense. Where dark matter is sparse, galaxies are sparse. The cosmic web is not just a web of galaxies. It is a web of dark matter with galaxies strung along the filaments like lights on a wire. The dark matter came first, the galaxies followed. Without dark matter, the universe would look nothing like it does. The structures we see today, the clusters, the filaments, the voids, all of it is the result of dark matter pulling normal matter into place over billions of years. Dark matter built the framework, gravity did the work. And we, the products of stars and planets and billions of years of cosmic evolution, are living inside the framework without being able to see it. That brings us to the philosophical weight of the 94%. 4 to 5% of the universe is made of ordinary matter. The stuff we are made of, protons, neutrons, electrons, atoms that can bond together to form molecules, molecules that can organize into structures, structures that can become rocks, oceans, stars, planets, people. The rest, the overwhelming majority, is something else, something that does not form atoms, something that does not bond, something that does not organize into complexity. Dark matter clumps under gravity, but it does not do anything beyond that. It does not shine, it does not heat up, it does not cool down. It does not interact with itself in ways that would allow it to collapse into dense objects like stars or planets. It just drifts, invisible and inert, shaping the universe through gravity alone. Dark energy is even stranger. It is not a particle. It is not a field in the way physicists usually use that term. It is a property of space itself, and it does not clump at all. It is uniform, everywhere, always. The combination of dark matter and dark energy defines the universe. They dictate how it formed, how it evolved, how it will end, and we cannot see either of them. We cannot touch them. We cannot measure them directly. We can only infer their presence from the effects they have on the 4% we can see. That is a humbling realization. For most of human history, we assumed the universe was made of the things we could see: earth, water, air, fire, then atoms, then protons and electrons and neutrons, then quarks and leptons and bosons. Each time we looked closer, we found smaller building blocks. And each time, those building blocks were made of ordinary matter, the kind of matter that interacts with light, the kind we can study in labs, the kind that makes up our bodies and our planet and our stars. Then in the 20th century we realized that ordinary matter is the minority. Most of the universe is not like us. It is not made of the same stuff. It does not follow the same rules, and it is completely inaccessible to our senses. If dark matter particles are passing through your body right now, and they almost certainly are, you would never know. They do not interact with the atoms in your cells. They do not trigger nerve signals. They do not leave a trace. You are transparent to them, and they are invisible to you. The same goes for dark energy. It is everywhere, in this room, between the atoms in the air, in the gaps between electrons and nuclei. It is pushing space apart at every point in the universe, and you feel nothing. Because the effect is too small and too slow to register on human scales. Dark energy does not push on objects, it pushes on space, and space at the scale of a room or a planet or even a galaxy resists. Gravity holds things together on small scales. Dark energy only wins on the largest scales, where the distances are so vast that gravity weakens and the cumulative push of dark energy becomes dominant. The interplay between dark matter and dark energy has shaped the entire history of the cosmos. In the early universe, dark matter clumped together under gravity, forming the seeds of structure. Normal matter followed, falling into the dark matter halos and forming the first stars and galaxies. For billions of years, gravity was in control. Dark matter and normal matter worked together, building larger and larger structures. Galaxy clusters formed. Filaments stretched across hundreds of millions of light years. The cosmic web took shape. Then, about 5 or 6 billion years ago, dark energy crossed a threshold. The universe had expanded enough that the density of matter, both normal and dark, had dropped below a critical point. Dark energy, tied to the volume of space, stayed constant, and it began to dominate. The expansion started to accelerate. Gravity could still hold galaxy clusters together. It could still bind galaxies to each other in small groups. But on the largest scales, dark energy won. The filaments started to stretch. The voids started to grow. And the universe entered the phase we are in now, where expansion is speeding up and will continue to speed up indefinitely. Dark matter built the structure. Dark energy is tearing it apart. Both are invisible, both are poorly understood, and both are in control. The philosophical implication is unavoidable. The majority of existence is beyond our direct perception. We can infer it, we can map its effects. We can build models that predict how it behaves, but we cannot see it, we cannot touch it. We cannot bring it into a lab and study it the way we study normal matter. The universe is fundamentally unknowable in the most direct sense. We are living inside a cosmos where 94% of the content is hidden from us by the basic laws of physics. Dark matter does not emit light. That is not a limitation of our telescopes. That is a property of dark matter itself. Even if we built a telescope 1 billion times more powerful than Webb, it would not help. Dark matter does not interact with photons. There is nothing to detect. The only way we know it is by watching how it bends space and pulls on galaxies. Indirect evidence. Shadows on a wall. Dark energy is the same. We cannot detect it directly. We can only measure its effect on the expansion of the universe. And even that measurement is hard. It requires precise observations of distant supernovae, careful calibrations and models that depend on assumptions we cannot fully test. The uncertainties are large. The tensions between different measurement methods are real, and the more we learn, the stranger the picture becomes. The James Webb Space Telescope has not solved the dark matter problem. It has not told us what dark matter is made of. It has not detected a single dark matter particle. What it has done is give us the sharpest view yet of how dark matter is distributed across the universe. It has shown us the invisible scaffolding in unprecedented detail. It has mapped the structure that galaxies are built on, and in doing so, it has reminded us just how much we do not know. The map Webb produced is beautiful. It shows clumps and filaments and voids, all inferred from the bending of light. It is a snapshot of the dark sector, captured indirectly through the distortion of the visible sector. But it is not a photograph of dark matter. It is a ghost, a trace, a fingerprint left behind by something we cannot see. And that is as close as we are going to get, for now, maybe forever. The humbling part is not just that we do not know what dark matter is. It is that the universe does not care whether we know. Dark matter does not need to be understood to do its job. It holds galaxies together. It shapes the cosmic web. It has been doing that for more than 13 billion years, long before humans existed to wonder about it. And it will keep doing it long after we are gone. The universe is not designed for us to understand. It is not obligated to reveal its secrets. We are observers, late arrivals to a cosmos that was already ancient when our planet formed. And most of what that cosmos is made of is invisible to us. Not because we lack the tools, because the stuff itself does not interact with light. It is fundamentally, irreducibly hidden. That is the reality. 94% of the universe is dark, and we are standing in the remaining 6% trying to make sense of shadows. The irony is that the 4% we can see, the stars and galaxies and planets, all of it exists because of the 94% we cannot see. Without dark matter, galaxies would not have formed. Without dark energy, the universe would have collapsed back on itself billions of years ago. The visible universe is a side effect, a byproduct of the dark sector doing its work. We are living in the scaffolding, unaware of the structure holding us up. And now, thanks to Webb, we can at least see the shape of that structure, even if we cannot touch it. The map is not the territory, but it is the best map we have ever made. And it is a reminder that the universe is larger, stranger, and more complex than we will ever fully grasp. Most of it is beyond our reach, most of it always will be, and yet here we are, a species of curious primates standing on a rocky planet, pointing telescopes at the sky, trying to understand a cosmos that is 94% invisible. That takes a certain kind of audacity, or maybe desperation. Either way, we keep looking, keep mapping, keep asking questions we might never be able to answer, because the alternative, accepting that the universe is mostly unknowable and moving on, is not an option. We are small, we are temporary, we are made of the leftover 4%, but we are here, and for now, that is enough to keep trying. Even if the vast majority of existence remains forever out of reach, hidden behind the veil of the unknown, the invisible scaffolding we will never touch, you are transparent to the universe. Right now, as you sit here, dark matter particles are passing through your body, billions of them, maybe trillions, drifting through the atoms in your cells, through the chair beneath you, through the floor, through the earth itself, and out the other side without interacting with a single particle of ordinary matter along the way. You cannot feel them, you cannot see them, you cannot measure them directly, and yet they are there, streaming through you at every moment, part of the invisible scaffolding that holds galaxies together. Dark energy is doing the same thing. It is here, in this room, between the atoms in the air you are breathing, pushing space apart at every point in the universe, including the space between your hand and the screen you are looking at. The effect is too small to measure on human scales. Gravity wins here. But out there, Beyond the galaxy clusters, beyond the filaments of the cosmic web, dark energy is tearing the universe apart, and you feel nothing, because the universe does not need you to feel it. It does not need you to understand it. It has been doing its work for 13.8 billion years without asking permission, without waiting for a species of curious primates to evolve on a rocky planet and start pointing telescopes at the sky. The universe is not built for us. It is not designed to be comprehensible. It is not obligated to make sense on human timescales or human scales or in ways that fit comfortably inside human brains. And yet here we are, trying anyway. The James Webb Space Telescope has given us the clearest picture yet of what we are up against. 93 billion light-years, 2 trillion galaxies, structures forming faster than they should, black holes appearing earlier than the models allow. A cosmic web stretching across the entire observable universe, threaded with dark matter we cannot see and pulled apart by dark energy we cannot explain. 94% of everything that exists is invisible, unreachable, fundamentally hidden from us by the basic laws of physics. We are living in the leftover 6%, trying to make sense of shadows, and the more we learn, the smaller we get. Not smaller in the sense of shrinking, smaller in the sense of perspective. Every time we thought we had the universe figured out, every time we thought we understood the scale we were dealing with, the universe got bigger. The stars were not fixed to a crystal sphere. They were suns scattered across vast distances. The Milky Way was not the entire universe. It was one galaxy among billions. The galaxies were not static. They were moving, receding, flying apart as space itself expanded. The expansion was not slowing down. It was speeding up, and the matter we can see, the stars and planets and gas clouds, all of it, is a rounding error compared to the dark sector. Every discovery has been a step backward, a zoom out, a reminder that the cosmos is larger, stranger, and more indifferent than we gave it credit for, and Webb has pushed that zoom further than any instrument before it. Stand outside on a clear night and look up. You see a few thousand stars, maybe, if you are far from city lights. Every one of those stars is in our galaxy. The Milky Way, our neighborhood. The Andromeda Galaxy, the nearest large galaxy, is 2.5 million light-years away. And on a dark night you can see it with the naked eye as a faint smudge. Everything else you see with your eyes, every pinpoint of light, is local. Cosmically speaking, you are looking at your front yard. The universe beyond that, the other 2 trillion galaxies, the galaxy clusters, the superclusters, the filaments of the cosmic web, all of it is invisible to the naked eye. Not because it is not there, because it is too far away, too faint, or too redshifted for human vision to register. You are standing on a planet that is 8,000 miles wide, orbiting a star that is 93 million miles away, in a galaxy that is 100,000 light-years across, in a universe that is 93 billion light-years wide, and you can see none of it without help. Your senses, the tools evolution gave you to navigate the immediate environment, to find food and avoid predators and recognize faces, are useless for seeing the cosmos. You are blind to the true scale of existence. We all are. The only reason we know any of this is because we built instruments that can see what we cannot, telescopes that collect more light than our eyes, detectors that sense wavelengths our brains cannot process, computers that analyze patterns too faint or too complex for a human to spot. We extended our senses, and what those extended senses are showing us is that we are smaller than we thought. Much smaller. The Milky Way contains somewhere between 200 and 400 billion stars. That is an estimate, not a precise count. Counting stars in a galaxy is hard when you are sitting inside the galaxy, but 400 billion is a reasonable midpoint. Our Sun is one of them, ordinary in almost every way. Not too big, not too small, not too hot, not too cold. Sitting in a quiet spiral arm about 26,000 light-years from the galactic center. Unremarkable. The galaxy itself is unremarkable. It is not the largest galaxy. It is not the brightest. It is not in a massive cluster. It is part of the local group, a small collection of about 80 galaxies, most of them dwarfs. The local group sits on the edge of a structure called the Laniakea supercluster, which contains about 100,000 galaxies. Laniakea is one of millions of superclusters scattered across the observable universe. We are not special. We are not central. We are not even in a particularly interesting part of the cosmos. We are in the suburbs, a backwater, a quiet corner where not much happens. And from that quiet corner, we have been looking outward, trying to map the rest of the universe and discovering that the rest of the universe is so large that our entire neighborhood, our entire supercluster, barely registers as a dot. The observable universe, that 93 billion light-year sphere, is not the whole universe. It is just the part we can see, the part whose light has had enough time to reach us since the Big Bang. Beyond that horizon, the universe continues. We know it continues because there is no reason to think it stops, no edge, no boundary. The universe does not need a wall. Space just keeps going. How far, we do not know. Some models suggest the universe is infinite. Others suggest it is finite, but so much larger than the observable part that calling it infinite is a reasonable approximation. If you could somehow teleport to a galaxy 40 billion light-years away and look around, you would see an entirely different observable universe. The galaxies visible from Earth would have vanished beyond your new horizon. New galaxies currently beyond our view would come into sight. The observable universe is not a fixed bubble. It is the view from here, from Earth, from now, and every other location in the universe has its own view, its own horizon, its own 93 billion light-year sphere centered on itself. The total universe, the whole thing, could be thousands of times larger than what we can see. It could be millions of times larger. It could be infinite. We cannot know, not yet. Maybe not ever. The observable universe is the only universe we will ever have access to, and even that is slipping away. Dark energy is accelerating the expansion. Galaxies beyond our local group are receding faster every year. Eventually, billions of years from now, they will recede so fast that their light will never reach us. The observable universe will shrink, not because space is collapsing, because the edges of what we can see are defined by how far light can travel in an accelerating cosmos. One by one, distant galaxies will redshift into invisibility, the cosmic web will dissolve, the filaments will tear, and the only galaxies left in view will be the ones gravitationally bound to the Milky Way. A few dozen galaxies. That will be the entire visible universe. Everything else will be gone, not destroyed, just beyond reach. That is the future dark energy is writing, and we are living in the brief window of cosmic history when the universe is still full, still connected, still capable of being mapped. A few trillion years from now, any civilization that exists will look out at a sky containing only their local cluster and assume that is the whole universe. They will have no way to know it was once larger. The evidence will have accelerated beyond their horizon. They will be cosmologically isolated, unaware that they are living in the ruins of a much larger structure. We are luckier. We are here now, when the universe is still visible, when the galaxies are still within reach of our telescopes, when the cosmic microwave background still carries the fingerprints of the Big Bang, when the light from the earliest galaxies is just now arriving, after traveling for more than 13 billion years. We are living at the only point in cosmic history when the full story of the universe can be pieced together. A few billion years earlier, and we would have missed the acceleration. A few billion years later, and we would miss the distant galaxies. We are here at exactly the right time to see it all. That is not a sign of cosmic favor. It is not destiny. It is just luck, timing. The accident of being born in an era when the universe is still revealing its secrets, and we are taking advantage of that luck. We built Webb, we pointed it at the sky, and we are pulling in data that will take decades to fully analyze, mapping the cosmic web, finding galaxies that should not exist, measuring the expansion rate, searching for the chemical signatures of life on distant planets, trying to understand what the universe is made of, trying to figure out where it came from, trying to answer the oldest question humans have ever asked. Why is there something instead of nothing? We do not have the answer. We might never have the answer, but we are asking the question, and that is significant. Not because asking the question changes the universe. It does not. The universe does not care whether we understand it, but asking the question changes us. It forces us to confront our place in the cosmos, our smallness, our insignificance. The fact that we are temporary arrangements of atoms on a small planet orbiting an ordinary star in an unremarkable galaxy in a universe so large that our entire existence, the entire history of our species, is less than a blink. We have been here for a few 100,000 years. Civilization has existed for maybe 10,000. We have had telescopes for 400 years. We have had the ability to leave our planet for 60. In cosmic terms, we just arrived. We are infants. And yet in that brief flicker of time, we have managed to map the universe. Not completely, not perfectly, but enough to know the rough shape of it. Enough to know that it is 93 billion light-years across and contains 2 trillion galaxies and is expanding faster than it should. Enough to know that most of it is invisible and that we are made of the leftover scraps. That takes a certain kind of audacity, or desperation, maybe both. We are a species that knows it is small and keeps looking anyway, knows it is temporary and keeps asking questions, knows the universe does not care and keeps trying to understand it regardless. There is a phrase that gets thrown around in cosmology: the universe becoming aware of itself. The idea is that matter, after billions of years of evolution, has organized itself into structures complex enough to think, to wonder, to ask questions about where it came from. Stars are made of hydrogen and helium fused in the cores of earlier stars. Planets are made of the heavier elements forged in supernova explosions. Life, at least on Earth, is made of carbon, oxygen, nitrogen, elements that did not exist in the early universe. They had to be created, built up over generations of stellar cycles, born, lived, died, exploded, scattered, reassembled, over and over, until eventually, on at least one planet, the chemistry got complicated enough to become biology. Biology got complicated enough to become consciousness, and consciousness got complicated enough to start asking where it came from. That is what we are. Stardust that learned to think. Atoms arranged in such a way that they can contemplate the cosmos they came from. The universe, through us, is looking back at itself, measuring itself, trying to understand itself. That is not a scientific statement. It is a poetic one, but it captures something true. We are not separate from the universe. We are part of it, made of the same matter, governed by the same laws, subject to the same forces, and yet we are different, because we can ask why. Rocks do not ask why. Stars do not ask why. Black holes do not ask why. But we do, and that makes us, if not significant in scale, at least significant in kind. The question that always follows is whether we are alone. 2 trillion galaxies, each one containing hundreds of billions of stars, each star potentially hosting planets. The numbers are so large that it seems impossible for life to have arisen only once, only here, only on Earth. The statistical argument is compelling. If the conditions that led to life on this planet, liquid water, organic chemistry, stable energy source, geological activity, if those conditions are common, and there is no reason to think they are not, then life should be common too. Maybe not intelligent life, maybe not technological life, but some form of life, bacteria, algae, something that metabolizes, reproduces, evolves. Webb is not a life detection mission. It was not built to find microbes on distant planets, but it is capable of analyzing the atmospheres of exoplanets, looking for chemical signatures that might indicate biological activity, oxygen, methane, molecules that should not be present in large quantities unless something is producing them and replenishing them. Because atmospheres are not static, they react, they equilibrate. If you find oxygen in an atmosphere and nothing is making more oxygen, the oxygen disappears. Earth's atmosphere is 21% oxygen because life, specifically photosynthetic organisms, has been pumping oxygen into the air for billions of years. Take the life away and the oxygen vanishes in a geological eye blink. If Webb finds oxygen or some other biosignature in the atmosphere of a planet orbiting a distant star, it will not be proof of life. It will be a hint, a suggestion, a reason to look closer, but it will change the conversation, because it will mean we are not alone. Or at least, we were not always alone. Life could have existed elsewhere and gone extinct. Life could exist now and be microbial, invisible to us until we develop better tools. Life could be common, but technological civilizations rare, or short-lived, or self-destructive, or so different from us that we would not recognize them even if we were looking directly at them. The universe is large enough to contain all of those possibilities, and more. What Webb has done, what every deep field image has reinforced, is make the statistical case for life elsewhere overwhelming. Not certain, not proven, but plausible in a way that feels undeniable. 2 trillion galaxies, hundreds of billions of stars per galaxy, planets around most of those stars, some of them in the habitable zone, some of them with water, some of them with chemistry. The ingredients are there. The question is whether the recipe is common or rare, whether life is an inevitable consequence of the right conditions or a fluke that happened once and might never happen again. We do not know, but the numbers are in favor of life being out there, somewhere, in some form. The silence, the fact that we have not detected any signals, any messages, any signs of technological civilizations could mean life is rare. Or it could mean we are not looking in the right places, or at the right times, or in the right ways. Or it could mean that civilizations, when they arise, do not last long enough to overlap with each other in time and space. The universe is 13.8 billion years old. Human civilization is 10,000 years old. Technological civilization capable of sending signals into space is less than 200 years old. If another civilization existed a billion years ago and died out, we would never know. If another civilization will exist a billion years from now, they will never know we were here. The window of overlap, the chance that two civilizations exist at the same time and are close enough to communicate, might be vanishingly small. The universe could be full of life, full of intelligence, full of civilizations. And all of them could be isolated, separated by time and distance, never aware of each other. That is lonelier than being alone. Because it means the universe is teeming with consciousness, and none of it will ever meet. Webb cannot answer that question. No telescope can, not yet. But every image it sends back, every galaxy it maps, every early structure it finds forming faster than expected, expands the search space, pushes the boundaries of what we know, reveals more of the cosmos. And the more we see, the clearer it becomes that the universe is not hostile to life. It is not designed for life, but it is not hostile either. It is indifferent. The conditions that allow life to arise, stable stars, rocky planets, liquid water, organic chemistry, those conditions exist. They exist here. They likely exist elsewhere. The universe is not trying to create life, but it is not trying to prevent it either. Life is a side effect, a consequence of chemistry and time, and if it happened here, there is no reason to think it could not happen somewhere else. That does not make us less special. It makes the universe more interesting. Because if we are not alone, if there are other consciousnesses out there, other minds asking the same questions, other civilizations building their own telescopes and pointing them at the sky, then the universe is not just a collection of galaxies and stars and dark matter. It is a place where matter has learned to think, in multiple places, in multiple ways. That is extraordinary. Not because it makes us significant, but because it makes the universe significant. The cosmos is not just vast, it is alive, or at least parts of it are. And those parts, however rare, however scattered, however brief, are the parts that matter, because they are the parts that can wonder, that can ask, that can look at the night sky and feel small and keep looking anyway. The paradox is that our insignificance is what makes us significant. We are small, temporary, made of atoms that will one day be scattered back into the cosmos. Our planet will be consumed by the sun in a few billion years when the sun exhausts its hydrogen and expands into a red giant. Our galaxy will collide with Andromeda in about 4 billion years, a slow-motion merger that will reshape both galaxies and fling stars into new orbits. The sun, or whatever is left of it, will drift into a different part of the merged galaxy. The solar system, if any of it survives, will be somewhere else. Eventually, trillions of years from now, the last stars will burn out. The universe will go dark. Black holes will evaporate, and all that will be left is a thin soup of particles spreading through an expanding void. Everything we have ever known, everything we have ever built, will be gone, erased, forgotten. The universe will not remember us. It will not remember anything, because memory requires structure, and the heat death is the absence of structure. That is the ultimate fate, not a dramatic end, just a slow fade into nothing. And knowing that, knowing we are temporary, knowing the universe does not care, we keep going, we keep building, keep learning, keep asking, because that is what conscious beings do. We create meaning in a universe that has none. We find significance in our insignificance. We look at the cosmos, see how vast and indifferent it is, and decide that understanding it matters anyway, not because understanding changes anything, but because understanding is what we do. It is what makes us human, or conscious, or whatever word you want to use for the thing that separates thinking matter from non-thinking matter. The James Webb Space Telescope is not just a machine, it is an expression of that drive, the drive to see farther, to know more, to understand where we came from and where we are going. It cost $10 billion and took 25 years to build. Thousands of people worked on it. Engineers, scientists, technicians, people who will never be famous. People who spent their careers designing a single component, testing it, making sure it would survive the launch and the deployment and the harsh environment of space. And it worked. Every fold unfolded, every motor fired, every mirror segment aligned. And now it is out there, sitting at L2, staring into the deep field, pulling in photons that have been traveling for 13 billion years and sending them back to us so we can see what the universe looked like when it was young, so we can map the cosmic web, so we can measure the expansion rate, so we can search for life, so we can ask whether we are alone, so we can understand our place in the cosmos. That is what Webb is for, not to make us feel significant, to show us the truth. And the truth is that we are small, incredibly, almost laughably small, a single species on a single planet, in a single galaxy in a universe containing 2 trillion galaxies. We are a footnote, a rounding error, a speck. And yet we are the speck that built the telescope, the speck that decoded the cosmic microwave background, the speck that figured out the universe is expanding and that most of it is invisible, the speck that mapped the scaffolding we cannot see, the speck that keeps looking, keeps learning, keeps asking, even though the universe does not care. That is the paradox. We are insignificant by scale and significant by action, small by measure and large by ambition, temporary in duration and meaningful in intent. We will